de la Escuela de Verano Preparados de la Computacional, Computacionalista, en la comunidad Javeriana y de Univash. Hoy tenemos dos invitados, que son Pavel y Marco, a quienes quiero agradecer de antemano por haber venido hasta Cali, desde sus respectivas ciudades, a acompañarnos en esta escuela de verano. Y también quiero aprovechar para agradecer a Frank, que fue la persona que organizó esto, que hizo los contactos y que básicamente ha servido de anfitrión tanto a Marco como a Pablo. Hoy en la mañana vamos a tener una presentación o dos presentaciones sobre el mismo tema por parte de Pavel, por la tarde hablará Marco. Y los temas hoy en la mañana son modelamiento probabilístico de sistemas. Ustedes van a ver una forma de explicar sistemas usando probabilidades. Sistemas de transición, sistemas en general basados en probabilidades, y por la tarde van a ver un tema distinto que son session types, los tipos de sesión. So I'd like to thank you, Marco and Pavel, for being here, and we are in your hands.
Thank you very much. Thanks. It's a real pleasure to be here, as I said yesterday. So, thank you for coming back. So today is going to be more fun than yesterday, I think. But first, I wanted to go over some of the things we said yesterday. So the main concept really of this presentation is this notion of a channel. Right, so we saw an example yesterday. I'll just give you a quick, very quick rundown of what we said yesterday. So remember that a channel is something that is a function from a set to the set of probability distributions or sub-probability distributions on a set. Right, so our example here was Professor Frank, who can be in 3 moods, and this influences the chances of him giving particular marks, right? So when Professor Frank is angry, he's more likely to give lower marks than when he's happy. Okay, so the cool thing about channels is that they have an algebra. Okay, so they can be composed in 2 different ways. So one way is the sequential composition that we went through yesterday. And you recall that the example that we gave was that Professor Frank's hunger influences his mood. And so this can itself be a channel, be described as a channel, sort of from the set of states hungry and full to the set of states angry, normal, happy. So when Frank is hungry, he's half the time he's going to be angry and half the time he'll be normal. And when he's full, he'll be half the time he'll be normal, half the time he'll be happy. And the idea is that now we can sort of multiply out this middle state of the moods to just obtain a channel, a composite channel from hungry, full to fail, pass distinction, right? So we did the calculation. So, when Frank is hungry, he's going to, again, give, as expected, more likely give lower scores than when he is happy, when he's full. Okay, so that's one way of composing channels. This is like a sequential composition of probabilistic channels. The other way is this kind of a parallel composition, where essentially the idea is that we have 2 channels and we obtain a channel. So we have a channel from X to Y, we have a channel from U to V, and we obtain the product channel from X times U to Y times V. Okay, and you can really think of these as these 2 channels operating independently. This is like a parallel composition. Okay, and I'll just remind you, we went through some very particular examples of channels. So when the domain of the channel is a singleton set, so a set with just one element, then a channel is just the same thing as picking a sub-probability distribution. Okay, so these things are sometimes called states. We also saw how ordinary functions can be seen as channels. So these are what we call deterministic channels. And it's very kind of obvious how you do this. Well, if I give you a function from X to Y, then I can give you a channel that just given an X produces f of X with probability 1. Okay, so it's deterministic. So an example of a deterministic channel was the identity that we we spoke about yesterday. So the identity channel is something that takes an X and just produces with probability 1 X. Okay, so it's an example of a deterministic channel. And the cute thing is that it forms an identity for composition, right? So if you pre-compose F with identity on its domain, or post-compose with the identity on its codomain, then you just get F back. Okay, so another special channel is this copy channel, which again is a deterministic channel. And all this does, it seems kind of trivial, but it's actually very useful, as we'll see in later examples today. So what it does is it takes an X and produces with probability 1 the pair XX. Okay, so the intuition is that this just copies the data. Another channel is discard. Okay, so this is a channel from X to the one element set to the singleton. And it kind of just does the most obvious thing. It's just given any X, it produces this element of probability 1. Okay, I'm going to maybe come back to these questions later. I want to get to the fun stuff as quickly as possible today, because you'll see how these channels are used in practice. But maybe I just want to, we didn't get to the slide yesterday, so maybe I'll spend a little bit longer on the slide. Because yesterday we spoke about marginalization, right? So marginalization was this process where I give you a joint distribution and I throw away one of the factors to get a distribution on just the other factor. Okay, and the cute thing is that I can see now marginalization as a particular special case of composing channels, right? So a joint subdistribution, remember, it's well, you can see it as a channel. It's a special kind of channel. It's a channel from 1 to X cross Y, right? So now we also have this channel called discard, which intuitively just throws some information away. Okay, so if I discard and I multiply with the identity on Y, I get a channel of this type, but 1 times the Cartesian product 1 times Y was just the same thing as Y, right? Okay, if you're going to be very careful, it's an isomorphism, but there's no harm in just equating these two sets. And similarly, I can discard the second factor to get something from X times Y to X. Okay, so now if I take a subdistribution, a joint distribution, and I compose by discarding one of the factors, then I get a subdistribution on Y. And similarly, if I compose with this guy, I get a subdistribution on X. And it turns out that when you do the maths, when you do the calculations, these are just exactly the same as marginalizing. So I have one more special channel. This is the final special channel. And again, it's very simple. It's, again, an example with a deterministic channel. And the idea is that it operates on Cartesian product and it's going to swap 2 elements. Okay, so swap X times XY on the pair XY just gives me YX with probability 1. Okay, so the intuition is just it swaps the two factors, the two components of the pair. And it's not very difficult to see now that if I compose swap again with swap, I just get back the identity. Okay, because if I swap twice, I get back to where I started. Okay, good. So are there any questions about channels before we continue? No? Okay, good. So I want to now introduce a diagrammatic notation for channels. Okay. So first of all, I just want to say a few words about category theory. So I'm not even going to define what a category is in this presentation, but the diagrams that you'll see, they come from category theory. But maybe it's just going to be interesting for you just to understand a little bit about what category theory is. So category theory is an abstract part of mathematics, and I think in a very kind of intuitive, high-level way, you can think of it as uncovering sort of common constructions in different parts of mathematics. Okay, so it's like almost like in the 90s, when I was a student, the hot thing was object-oriented programming and something called design patterns. I don't know, I don't think this is really very popular anymore. Who's heard of design patterns, just out of curiosity? Okay, a few people. I guess you know about, I guess you probably know something like model view controller, right, and MVC. That's an example of a design pattern, right? So it's something that, like it's a coding principle, it's a way of organizing your codes in a way in which you see time and time again in many different applications, right? And so that's kind of for programming, but for mathematics, you can make similar observations, right? That similar kinds of constructions happen in algebra, similar constructions happen in topology, etc. And so category theory tries to pull these things out and study them at an abstract level. Okay, so as I said, I'm not going to really get very deep into category theory. In fact, as I said, I'm not even going to define what a category is, but I'm just going to throw some terms at you just so that I feel better myself. So we use an important part of category theory called symmetric monodal categories. And symmetric monodal categories are talk about things that you can compose sequentially and in parallel, and you can swap, right? And that should ring a bell, right? Because channels, we saw we can compose them sequentially, we can compose them in parallel, they have identities, and we can swap, right? So channels are an example of such a thing. And any symmetric monodal category comes with a nice intuitive diagrammatic syntax called string diagrams. So this is what I'm going to talk about for the next few minutes. And in particular, we're going to use string diagrams in special kinds of symmetric monodal categories called partial Markov categories. And it turns out that channels come together to form one of these animals. And again, I'm not going to define it, but it's an interesting thing maybe for you to know about. And if you're interested, some of these references that I gave at the start yesterday talk about these in more detail. Okay, so let's jump right into the diagrammatic notation, right? So I'm going to draw a channel from X to Y as something like this. Okay, so it's a box labeled with the name of the channel. On the left, I have the input, which is drawn as a wire. I'm often going to label the input, the wire, with the kind of type that the wire is. And then the output again is a wire, and its type is also drawn. Okay, so that's the notation for a channel. And you're not going to be very surprised that to compose channels, so if I give you a channel from F, so F from X to Y, so something like this, and another channel G from Y to Z, so something like this, the composition, F and G, is just drawn by connecting the wire. Okay, and now you see I have something from Y to Z. Okay, so very, very simple. And now, what about parallel products? Well, given a channel F from X to Y and a channel G from U to V, the product will just be drawn as stacking the two boxes on top of each other. Right, so one thing you should notice is that when I have two wires coming in, the two wires, so X times U is just the same thing as X on top of U. It's just two wires. Okay, so this is again very intuitive, right? It captures this idea that this is some kind of parallel composition. These two boxes don't interact. And we know that that's how we also define the product of channels. Okay, so some more things about string diagrams. So the identity, so the singleton sets, the set with just one element, we're not going to draw it as a wire. We're just not going to draw it at all. Okay, so we saw that we can see distributions as special kind of channels from 1 to X, right? And I'm going to have a special notation for these. Instead of drawing them as a box, I'm just going to draw them as these kinds of half circles. And technically, this is a channel from 1 to X, right? But as I said, I'm never going to draw ones. I just don't draw a wire for one. Okay, so this is just the same. Whenever you see a picture like this is a subdistribution on X. Okay? So yet another convention is identities. So identities don't get a box, they are simply drawn as a wire. Okay, so the identity channel, so the channel, remember, the identity just takes an X and gives me the subdistribution, which is, just returns an X 100% of the time. So this is just drawn as a wire. And maybe not surprisingly, we're going to draw the swap channel, so the channel that just swaps the two parts of the pair as something like this. Okay, so something where the wires cross. Okay, so this is all very nice. So now basically, if I give you an expression with channels, composing them in parallel and sequentially, you should be able to just draw a diagram that represents that algebraic expression. Now, the cool thing about string diagrams, and something that I really like, is that they hide a lot of the bureaucracy, right? So I'll give you one example. This is just one example, but there are many examples like this. So if I give you a channel F from X to Y and a channel G from U to V, then I can take their products, right? I can take F times G, and it's my graphical notation for this channel is this, right? This is the power composition of F and G. Right, but I can also do some more weird stuff, right? So for example, I can first take the product of F with identity on U. Okay, so that gives me this diagram, right? Because you remember that we draw the identity as just a wire. I can take the product of the identity on Y with G, which gives me this part of the diagram. And then I can compose these two, right? So I get this diagram. And I can also do the opposite thing where I take the identity on X product with G and then compose with F identity on V. Okay, so I get, when I just look at these expressions, it's not immediately clear that they all define the same thing, right? But as pictures, they look very similar, right? And indeed, if you just picture in your mind, sort of moving these boxes along, so if I move F to the right slightly and G to the left, then I get this. And then if I keep moving G to the left and F to the right, I get this. Okay, in fact, all of these things are the same channel, right? Yeah, go ahead.
So I had a question related to the diagram. So we could say that as a general rule of thumb, if we're given two diagrams representing different compositions of channels, and we find that those two diagrams are the same up to sliding boxes across the wire, they're basically the same.
Yes, yeah, but this is something you have to prove, right? It's not, but it's true. And this is the beautiful thing about string diagrams. So the beautiful thing about string diagrams is, so this is some kind of a slogan that people often say, the only thing that matters is connectivity, right? So if everything is connected the same way, and you just deform the diagram in some way, then you get the same channel, and you can prove that they define in the end the same channel. Okay, this is why the graphical notation is so nice. I mean, I'll give you one more example maybe. So for example, I could take a channel F. I'm not going to draw the types, but and maybe I could take a channel G, and then I swap. Okay, so that's one way of specifying a channel. Or maybe let's make it even more interesting. Let's put an H here. Okay, and now you see I could try and slide the H over here. Okay, so, and maybe I'll slide the F down, right? So here I get an F down here. Let's say we keep the G over here, or we slide the H over here. Okay, so this goes back to what you were saying, right? So these two diagrams have the same connectivity. You can just get from one to the other just by sliding things along. And in fact, they do define the same channel. Even though if I was to write this algebraically, it wouldn't be very obvious, right? So this is why I really love string diagrams, because they're intuitive, but they're also rigorous, right? So these are not just pictures. So when I was a student, I remember going to all kinds of classes in which people were showing us pictures to others, like meant to give you some intuition, right? But they're only pictures. The pictures were not really, didn't really have a formal mathematical meaning. The pictures were there only to give you some kind of intuition about what's really going on. So the beautiful thing about these is that these are not just pictures, right? So they are pictures, and they give us the nice things that pictures give us. They give us intuitions, but they are formal mathematical objects, right? So each of them has a very fixed, rigorous meaning mathematically, and that's very important. And please, if you have any questions, just interrupt.
Pavel, just to clarify, now that you mentioned this, in the product, does it matter which diagram is on top and which one is below? I mean, can you swap them?
No, so that does matter, right? So that's, we need to know, because, when you write a function, for example, and the function takes 2 arguments, you need to know which one is the first argument and which one is the second argument, right? So this is why the order of the wires matters. And indeed, this is why we have an explicit swap, right? So sometimes it's convenient to reorder things, but you really then need the explicit swap to do this for you. Thanks. Okay, any other questions?
Okay, so I'm trying to imagine these boxes like not as channels or as something else like functions or something else. So can they be something else?
Very good question, Marco. Yes, and so they can be. So as I said, so string diagrams are a diagrammatic notation for something called symmetric monoid categories. And it turns out that channels form a symmetric monoid category, but functions also do. Right, so I can also just think of these as normal functions. Well, normal functions, we already know we can consider them as special kinds of channels, they're deterministic channels. But yes, so all of these sorts of functions, and in fact, there's all kinds of examples of symmetric monoid categories. So this diagrammatic syntax in the end is very, it's very useful. Like it has many different uses. And I actually kind of think of it. So when I was a student, when Frank was a student, when Marco was a student, we were all studying things called process algebras. They don't really exist anymore, I don't think. but the idea is that you really want to understand what can we, because it's a very common situation that you have processes with some computational meaning that you want to compose them sequentially and you want to compose them in parallel. Okay, and I really think of string diagrams as some kind of a very general process algebra, right? It really captures these two notions. Okay, so that's a very quick introduction to string diagrams. Now I want to get into some very particular features of string diagrams for channels. Okay, so in particular, copy gets a special feature. So copy, remember, is something that goes from X to X cross X. And this is the way we're going to draw copy. So it's kind of like a wire that just splits off. Okay. And it turns out that actually copying, it's not very difficult to prove, that it's associative or co-associative and co-commutative. Okay, and this can be expressed with equations between diagrams. So this is another really nice thing about diagrams, because diagrams are now formal mathematical objects. We can write equations. So for example, if I copy and I copy again on the first leg, this is the same thing as copying and copying on the second leg. So this is what I mean by copying being associative. And if I copy and I swap, this is just the same thing as copying. I can't tell the difference between the two things that I copied. Okay, so the nice thing about this kinds of equations is that whenever you see this guy inside a diagram, you can just replace him with this guy. Okay, so this is it gives you sort of a way of reasoning diagrammatically. So we're not going to see too much examples of this in this lecture, but this is a very interesting and an important part of string diagrams.
Pavel, just
yes.
Out of curiosity, if you wanted to generate like infinitely many copies, do you have a construct for specifying infinite behavior or something?
So here, well, as I said, for the purpose of this whole presentation, we first of all, we made several finiteness assumptions, right? So our channels, so our distributions are always discrete distributions on finite sets, okay? And just by the way you draw string diagrams, you're going to have, you know, in general, a string diagram is going to look, I mean, in general, like a string diagram is going to look like a box with some stuff in it, with some number of wires coming in and some number of wires coming out, right? So maybe m wires coming in and n wires coming out. So these are always finite numbers. Okay, so we don't have a notion of a string diagram with an infinite number of inputs. So something like an infinite Cartesian product. So yeah, so for the purpose of this talk, we stick to everything stays finite.
So you're introducing some structural equivalences for these string diagrams, right?
Yes.
Is there a notion of canonical representation for a string diagram that you prefer, or that is not important in this field?
Well, that's a very good question. So we do have underlying because yeah, so diagrams can be seen in 3 different ways. Okay, well, at least in 3 different ways. One way is the way I introduced it. I said, I'm going to give you a picture for everything, for what a channel is, how composing channels works, etc. And so then, essentially by doing this, I gave you a recipe that turns a term into a picture. Okay, so in this way, all I'm really saying is that this pictorial representation gives me another way of representing an algebraic term. And the nice thing about that is that it makes apparent a lot of equalities that are kind of structural, right? So that's one way of looking at it. So, and this is actually the way I normally do things, and I just think of these diagrams as a special kind of syntax. It's a 2-dimensional syntax, and in fact, when you look at its mathematical properties, just like, you know, syntax itself is a free thing, these also are a free thing, but it's, instead of being 1-dimensional like syntax, it's a 2-dimensional thing, okay? So it's syntax. You can also think of diagrams as topological things, okay? So actual drawings in 2-dimensional real space, okay? And then you can really think of these things as topological things. You can slide them around and prove theorems that, you know, when you slide things around, you preserve equality, okay? Which is very nice. So mathematicians like this approach. Another approach, the third approach that I'm aware of, is you can think of them as combinatorial objects, okay? So you really think of them as some kind of graph, you know, a set of nodes, set of edges, and connectivity maps, okay? And when you represent a string diagram like this, then you get a canonical representation, okay? Because you really then all that captures is the connectivity. And as I said, the connectivity is the important information. Now, of course, that only works for the basic set of equations. As you add more equations, then this becomes a rewriting system. Like then it really depends on the situation whether it has a normal form or not. But yes. Well, I mean, just like for normal rewriting systems, no, right? But you might get lucky. You might get a special system that you understand, and then you can prove that you know, let's say, you know, you have a normal form, you orient the equations in a particular way so that you get, you know, a confluent terminating system. Thank you. Okay, so that's copying. That's how we draw copying. Next, I want to talk about how we also have a special picture for discarding. So discarding is just looks like this. So from X, we just kill it. And in fact, discard provides a co-unit for the copy in the following sense, right? So if I copy and I throw away one of the copies, I just get the same thing as identity, and it's the same thing as if I threw away the second copy too. Okay, so again, it's very simple. You can prove these. You know, the way to understand these equations is that if I translate this picture into the expression of channels, right? So this is copy followed by discard tensor identity. If I just do the maths, then I'm going to get the same thing as identity, and I get the same thing as if I did the maths for this.
I have a question. So regarding the notation for discarding a certain set, so the way it looks, it's if the channel diagram was like a sort of road, then this car will be like hitting the end of the road, right? So, but in that sense, that must also mean that diagrams have a sense of a certain sense or intuition of flow, like in which direction are the channels flowing. So I wanted to ask because at least for me, it is not that clear from just the representations we have seen. Um, in the representations we have seen, it's usually just left to right, but I
Yes.
wanted to ask you if there's any sort of formal notation to indicate the flow of these channel diagrams.
So that's a very good question. Thank you. Yes. So in this entire course, we're always going to flow from left to right. Okay. But in fact, it's a very interesting when as you play with the string diagrams, there are many situations in which the flow is a little bit less clear. Okay. So I personally don't like to draw arrows. I don't like to say inputs and outputs, right? So somehow the fact that it's inputs and outputs is because channels themselves are very much oriented. Channels go from a set to distributions, right? So it's true that for the purposes of this talk, we always go from left to right. Okay, thank you. Okay, so I just have one little example before we start talking about applications. Okay, so I want to show you how we draw marginalization. So recall that a subdistribution is just a distribution on x cross y, which in pictures just looks like this. Okay, so this is a distribution on x cross y. And now if I want to marginalize the y, well, I just kill it. Okay, if I want to marginalize the x, I just kill it, right? So these are two pictures for the two ways of marginalizing a joint distribution. Okay, so that was a very fast tutorial in how to draw pictures. So let's start now. I think now we have enough maths. We've done enough work to actually have a bit of fun. Okay, so I want to model. I've got two problems to model for you. I want to start with the Monty Hall problem. Who's heard of the Monty Hall problem? Okay, many people. Good. So first of all, let me describe the problem. So it's a really famous problem, right? It's famous because it's an example of a probabilistic puzzle that challenges our intuition. If you've already seen it, probably you've rewired your brain to make it really obvious why it's the case, right? But when you see it for the first time, many people get really stumped. I think naturally human beings are not that good at reasoning about probabilities. So it's something that we kind of need to teach ourselves. And in fact, when you read the story of this problem, many people were angry, like they didn't believe the solution, right? So it's like, and several famous scientists were unconvinced. They had to run simulations to convince themselves that this actually is true. Okay, but let's go through the problem so that everyone understands what it is. Okay, so there's a game show. Okay, and the game show works like this, right? So we have 3 doors, and behind one of the doors is a car, and behind the 2 other doors is a goat. Okay, and the idea is that the contestant, let's say it's us, we are the contestant, we have to choose one of the doors. Okay, so let's say, the game show host asked us, have you made a choice? We say yes. Let's say I choose door number 1. Okay, so the host says, okay, fine, and doesn't open the door. Okay, so we don't know what's behind door number 1. It could be a car, it could be a goat. And what happens next is the game show host opens one of the other 2 doors, so in this case, door number 3, and shows us, oh, look, behind door number 3, there's a goat. And now the host says, are you sure you want to stay with door number 1? Or do you want to switch to door number 2? Now the question is, what should we do? Okay, so I'm hearing lots of switch. Who thinks we should stay? Who's gut feeling? Don't look at other people, because when I because when I first heard this problem, it's like, hey, I'm a lucky guy, you know. I chose the car. I'm not going to switch. The host is trying to fool me here, right? I'm going to stay with my belief, right? And that's, I think, for many people, that's the natural instinct. So the people who say switch are just saying this because they already know the problem. You have a question?
You can think of it like you have 1/3 of probability of picking the right door, right?
Yes.
So the probability says you're most probably going to pick the wrong door. So when he opens the other wrong door, the most common thing or intelligent thing to say is, well, probably I picked the wrong door at the start, so
Yeah.
he's telling me
Yeah.
what's the door with the car.
Very good, very good, very good. Yeah. So it's true that you should switch, right? And the way I explained to me, like I had to think about it for some time, and the way I explained to myself is very similar to what you said, right? So I say, at the start of the game, I had a 1/3 chance of picking the right door and 2/3 chance of being wrong. Okay. Now, if I was right all along, then I had a 1/3 chance of winning. But if I was wrong, then I win always, right? Because the host essentially showed me where the car is. So 1/3, 2/3. Okay, so you should switch. The lesson is you should switch. But maybe you're not happy with this explanation, right? Maybe maybe you don't believe me. Maybe you still feel like I made the right choice. Okay, so this is where I think let's actually try to model this using what we know, right? So, and first I want to start by talking about models. Okay, so theoretical computer science gives us many tools to model problems. Okay, so you probably learned some of this in various courses that you took, right? So things like automata, finite state machines, which have many, many different variants, which are useful for modeling different kinds of problems. So Petri nets, vector addition systems are things that use in concurrency theory to model concurrent systems. We have process algebras, process calculi, even things like what Marco was talking about yesterday. Things like something like toy Erlang. That's a kind of idealized programming language, right? It's something that you can model situations in real life programming languages. So what is a good model? Okay, so the idea is that we want to abstract away unnecessary detail. We want to throw away everything that's not relevant to the problem. We want to capture the core of the problem and give useful predictions and insights about the behavior of the system. So what are the kinds of useful insights or predictions? So maybe things like catching bugs, catching deadlocks, understanding how information could leak, security problems, etc. And very importantly, I think, maybe this sometimes is understated, is that these models should be transparent and easy to understand. They shouldn't be very complicated encodings. They shouldn't be questionable implicit assumptions that are made just because, I'm a PetriNet guy and this is how we do things in PetriNets. Okay, so now we have all of the pieces that I was playing around with this myself just a few days ago, so this is something that I put together myself. And the idea is we're going to model the Monty-Hall problem together using these string diagrams of channels. Okay, and just one more thing before we get started is I'm going to use, so these calculations, once you start, drawing complicated networks of channels, you don't want to do these calculations by hand. So I'm using a software library, which is in development. It's by Bat Jacobs and Kenta Cho, that performs calculations with channels. You can see it here. It's a Python library. And I'm going to give you code examples as we go on. Okay, so we have 5 minutes before the break. So maybe it will make sense to take the break now, and then I can just launch into modeling the Monty-Hall problem. So we don't have to stop after 2 slides. Okay, so we take a 15-minute break. Okay, so we come back here at 11:10. Okay. Are there any questions about the code or the function? Okay, so let's look at the story so far. Okay, so the story so far is we have the card distribution, the player choice distribution. Now we want to keep them around, right? We don't want to just open and forget about them. So we're going to copy them. So this is where the copy channels come into their own. The host opens a door, right? And the story so far is we have 3 distributions. One distribution on which door, well, we have one distribution, but it's a joint distribution, right? It's a distribution of the Cartesian product of doors with itself 3 times, right? Because there's the part where the host, which door the host opens, which door contains the car, and which door we chose. Okay, so that's the story so far, and you can generate the outcomes. I'm not going to go through this, but you just have to trust me that it's the right thing. Okay, but what we can do now is we can model the situation. What if the player chooses not to swap? Okay, so the player just says, I forget about this door that the host opened, so I did discard it, and I just stick with my original choice. I plug in my utility, and not surprisingly, you know, if I just discard this open, as if this open never happened, and we already kind of know this diagram really is very much similar to the diagram we've seen before. But anyway, we can just calculate what the value of this distribution is, and it's just the same as we said before, right? We win with one third of the time and lose 2/3 of the time because we ignored what the host did. Okay, so now let's see what happens if we do choose to swap. Okay, so switch now is going to be a box that takes in the door that was opened and the door that we chose, and it's going to pick the other door. Okay, because we chose to swap. Okay, so again, the code is pretty simple. So the switch function takes the open door, so the door that the host opened, the door that we chose. So if this open door is different from my door, then I'm just going to pick the other door, right? Because that's the door that remains closed, right? So that's the door that we're going to pick. Otherwise, we're going to return the always 0 state, right? Because this is some kind of an undefined state, right? Because there is no way that the host opened the door that we chose, right? That's outside of the scope of the game. So here we can just say 0, right? Undefined. Okay, so this is the entire string diagram now. We've just really modeled everything that happens in the game. The host opened the door, we chose to switch, and now we feed that choice that we've now made into the utility function. And as we said before, we win with 2/3 of the time and lose 1/3 of the time. Are there any questions? It's very simple, right? And it's I think it shows you the beauty of using this kind of diagrammatic notation. So actually, I have some interns at the moment which are working on a software package that allows you to draw these string diagrams, and we want to then generate automatically this underlying code and be able to play with these kinds of modeling. So because I did this myself, just preparing for this course, I actually drew these pictures myself, and then I wrote the code from the pictures, right? But this is, of course, can be automated because as we know, these pictures, these diagrams are rigorous things, and they correspond unambiguously to a particular channel. Okay, very good. So if there are no more questions, I have another well-known cute probabilistic puzzle where we're going to introduce a little bit more structure in order to capture it. Okay, and this is coming back to at the start of the lecture yesterday. I said that subprobability distributions are useful because they allow us to kind of model partiality, partial functions. Okay, so what I'm going to do is I'm going to introduce another channel called equality check. And I'm going to give it a special diagrammatic notation. Okay, so given a set X, we're going to define equality check that goes from X cross X to X. And the way it works is if X is equal to Y, we're going to return X with certain probability, with 100% probability. But otherwise, I'm just going to return the totally zero distribution. Okay, so this is kind of like saying undefined. So zero here means the distribution where all the factors are zero. Okay, and we're going to draw this as a string diagram as follows. So the cute thing, so these this is actually the work of my PhD students, Mario Roman and Elena Di Lavora, and they introduced this class of categories called partial Markov categories, and they had a paper at the LIX conference last year on this. So I'm using their work. So one cute thing is that together with copy, this partial equality check satisfies these things known as the Frobenius equations. Okay, and this is if you're seeing this for the first time, try to memorize this because it's somehow, for me, it's a very, very important equation. It says something very deep, I think, about equality. And it's been some kind of a recurring theme in my research. Like I always seem to run across the Frobenius equations. But basically, it says something very simple, that if I copy and then I equality check, it's the same thing as I equality check, then copy, and it's the same thing as I copy and then equality check. Okay, so that's the copy. And we're going to use that's the equality check. And we're going to use now the equality check to model another cute probabilistic problem. Okay, so this one maybe is a little bit more subtle than the Monty Hall problem. Okay, so we have 3 prisoners on death row. So 3 prisoners who have been sentenced to death. And let's call the prisoners A, B, and C. Now, the governor of this province has pardoned one of the prisoners at random. But only the warden knows who the prisoner is, the prisoner who is not going to be executed. And prisoner A asks the warden who is to be pardoned. The warden refuses to answer. Prisoner A then asks the warden who is to be executed, okay, which is a different question. The warden thinks for a while and says prisoner B. So prisoner A is happy because prisoner A thinks, okay, well, prisoner B will be executed, so I have a half a chance of getting pardoned. But is it true? Is it true that prisoner A is in any better situation? And in fact, what have we really learned? So have a think about it. I want you to, before we kind of launch into modeling this, I'll be happy to give you some time to think about it and tell me what you think. So, yeah, go ahead.
So I think this setup is both similar and different to the Monty Hall problem. Similar in the way that we're still trying to figure out what is the correct option and the chances that I have or that the prisoner A has to survive maybe. But also there's a fundamentally different thing about this setup, and it is that the governor has already pardoned one of the prisoners, and that fact cannot be changed. So it is kind of different to the Monty Hall problem.
Well, it's similar because the car is also behind one of the doors, right? So we know that the car is behind one of the doors. Maybe one, but you're right. They're very similar. They're very similar. They're subtle and they're slightly different in different ways, right? So one thing is that we're really fixed. So prisoner A and prisoner, we know that the warden has said prisoner B. So we know for sure that the prisoner B is to be executed. But in a sense, it's similar also to the Monty Hall problem because we know for sure then that one of the doors has a goat. Right, so you're right, it's similar, but I'll be happy. So what do you think? Do you think prisoner A has learned something useful? Do you think prisoner A should be happy, or what do you think?
Like, I think in an actual probabilistic distribution, if we were only thinking about that, then prisoner A, I believe he should not be happy, because that doesn't necessarily mean he's guaranteed.
No, but
to
is
be-
should he be happier than he was at the start?
Yes.
Okay. Any good? Thank you for that. Any other? Yeah.
Well, I think there's also a chance that the warden like is messing with his head. So I believe that the prisoner A really doesn't learn anything and is false hope.
Okay, so you think that prisoner A still has the same chances of being executed as he did at the start?
Yeah, because there's a chance that the warden lied to him. So there's.
Oh no,
still-
we're assuming that the warden doesn't lie.
Okay, so there maybe he can be a little bit happier, but it's not guaranteed.
Okay, thanks. Yeah.
Hi.
Hi.
I don't think it has a meaning towards the wording. I think everybody like ABC has the same level of it could be executed at no matter what. But I think the wording is kind of like the key, because they say he asked the question about pardon and then he say executed, and I think the program is looking forward to execute, not to pardon anybody. So he will give the answer about B because it's what is done.
Yes.
It's not about what is
But
pardoned.
we do learn something, right? We know for sure that prisoner B will be executed. So we have learned something.
Yeah.
The question is, have we learned anything about A or C?
I think that prisoner A is gonna be like pardoned, because I believe that if he wasn't the one that was going to be pardoned, the warden would have said to him that that he was going to be the one that was pardoned.
No, but the warden's not allowed to. The warden doesn't want to talk about who is pardoned. The warden only tells who is to be executed. Right? He refused to answer this question. So this is maybe the warden is messing with his head, but the warden doesn't lie.
Well, you can think of it like the prisoner A had again 1/3 of being the one who is pardoned.
Yes.
But now, knowing the prisoner B is going to be executed, he now has a one half of being pardoned or being executed.
Well, that's what prisoner A thinks. But so you think prisoner A is right to be happy?
Yeah. He's right to be happy because he now has more probabilities of being the one pardoned.
Okay, interesting. Any other question? Any other comments? Okay, good. So it looks like we need some modeling here, right? Oh, yeah, there's a question at the back. Maybe Frank.
Hi.
Hi.
So, like in the problem we see before, when we change the door, now changing we have like 2/3%, 2/3 probability or choosing the correct one. In this case, he has like 1/3 probability of being executed. When they reveal that the other one is going to be executed, he doesn't have like the change for changing, so he's still having 1/3% of being executed.
Yeah.
Even the other.
Well, what about
prisoner,
C? What about C?
He has 2/3 probability of being pardoned.
Very good. That's actually the correct answer. So thanks.
Thank you.
But it's not obvious, right? It certainly wasn't obvious to me. So some people are better at
analyzing these issues. So yeah, I'm going to tell you what the right answer is. So the right answer is that the probability, as you said. So what's your name? As Juliana said, prisoner A hasn't actually learned anything. So prisoner A still has 1/3 possibility of being executed. But we did learn something really interesting about prisoner C. So prisoner C now has 2/3 of a chance of being pardoned. And it's really not obvious, right? It's somehow counterintuitive. Okay, so let's model it and see the computer give us the right answer. Okay, so let's get onto the modeling. Okay, so again we have the pardon is a uniform state on prisoners, right? We don't know what decision the governor made. Now prisoner A, well, prisoner A is just going to be the deterministic distribution that returns prisoner A. Okay, because prisoner A is specified in the problem. Okay, so the warden knows who is to be pardoned. And the warden, the prisoner A comes to the warden and asks the warden the question. Okay, so let's model let's write the code for the warden. So warden answer. So warden is aware of who is to be pardoned and who is the asker. Okay, I wrote this code so that it's not hard-coded that it's prisoner A. So if pardon is equal to the asker, then then we know that the warden knows that this prisoner who's asking is to be pardoned. So the warden will just flip a coin and say one of the other two gets. We know that the other two will get executed, right? So, but the warden's not going to say both of them. The warden's going to pick one of the other two at random. Okay. Otherwise, prisoner A is to be executed. Okay. So the warden will just give the other prisoner, right? Because one of the prisoners is to be pardoned, so the third guy is to be executed. So this is just going to be a deterministic redistribution now that just picks the guy that's going to be executed. Yes. Is it clear? It's kind of uncontroversial. I think it's or at least I hope it's uncontroversial, just modeling the problem statement. Okay. So let's put everything together. And we get the following distribution now, right? So this is a distribution on a joint distribution on prisoners times prisoners. The first factor is the guy who's pardoned, and the second factor is the warden telling you who's going to be executed. Okay, so obviously, I mean, you can't be both pardoned and executed at the same time, so all of these diagonals are going to be 0, and you have different kinds of probabilities for the other cases, right? So that's the distribution. That's what fprob calculates. So are there any questions at this point? Shall we move on? Okay, so the next thing is kind of like the utility function we had before. So this is kind of a pardon check. Who's to be pardoned? So essentially, we're going to take as an input the guy who's to be pardoned and the warden answer. So if pardoned is the guy who's executed, then something terrible has gone wrong. So I'm just going to be undefined, and otherwise I'm just going to ignore what the warden said and return who's been pardoned. Okay, and it's kind of clear that I'm kind of totally ignoring the warden answer. So the possibility of being pardoned is just the same thing that we started with, so 1/3 for each of the prisoners. And in fact, when I was modeling, so I did this 2 nights ago, and I was trying to understand how can I model this properly, right? So this was my kind of first thing, and I went, what am I missing? What am I missing from my model here? So I'm kind of ignoring really what the warden said, right? So how can I bake this into the model? So what am I missing from the statement of the problem? Yeah. Well, I'm missing. So one thing that we're missing is the thing that we know what the warden said, right? So the warden said prisoner B, and that's kind of missing in this picture. Right, so let's try to include this. Sorry. Well, yeah, we could have just. I mean, this kind of is a silly function now that I think about it. We could have just discarded the word and answer and put the wire, but it still would have been the same distribution, right? But we're kind of missing something from the description of the problem. So this model doesn't quite doesn't quite include all the information that we were given, right? Because we know that the warden said prisoner B. Okay, so this is what I'm going to include here, right? So I'm going to say, so this is kind of, so prisoner B now is the the deterministic distribution that just returns prisoner B. Okay, and here I'm going to do an equality check on the warden answer and prisoner B. So in a sense, what I'm doing here is I'm restricting to only those runs in which warden says prisoner B. Okay. Now, when I run this using fprob, I see that, okay, well, 0 obviously has 0 chance of being pardoned, right? Because warden said B. Okay, so we know B has to be executed. So, but what we get is we get this relationship between A and C, that C is twice as big as A. Now, it's not quite 1/3 and 2/3 because this is a subprobability distribution and it's killed off some of the probabilities, but the ratio is the same, right? So after we normalize, so we know that prisoner C has twice the chance of A of being pardoned. After normalizing this, the distribution is just 1/3 A and 2/3 C. So it's exactly what Juliana said. Yeah, so that's sort of a little taste of using string diagrams to model things. And I hope that you, on the one hand, I think it's these models are very nice because they give us an intuitive overview of the communication patterns and within the sort of how the information flows in these kinds of problems. And on the other hand, they're not pictures, they have formal mathematical content, so they can be translated into code and evaluated. Okay, are there any questions? Yes, go ahead. Frank, we have a question at the back.
So maybe in an hypothetical case that C makes that question, that makes that C has less opportunity of being pardoned, so that like only A has less opportunity to be pardoned because he has made that question.
Yes.
Or yeah.
Well, if this situation, everything is very symmetric, right? So if this was C, then A would, and after the warden answered B, then we'd know that prisoner A had 2/3 of being pardoned. So everything is very symmetric.
Okay. Following up the question of my partner, don't you think, besides the fact that the math sort of adds up, don't you think that it's kind of counterintuitive? Because you just said that the analysis would have been the same if it was prisoner C, the one who asked, and prisoner B is still the one who is supposed to be executed. So from the perspective of prisoner A, no, from the perspective of both prisoners, if we sort of take very literally what's happening in this problem, you could very well say that in some sense asking the warden, even though the prisoner who was going to be pardoned had already been chosen, the very act of asking the warden and receiving an answer has somehow changed my probabilities.
Yeah, this is actually an extremely important comment, and I thank you for saying this, because there is this thing about, so essentially what's the magic thing that happened here, right? So the magic thing is that joint probability distributions carry a lot of information. Okay, they carry a lot of information that somehow entangles the different factors in a joint probability distribution. So you have these kinds of, maybe you've heard about quantum entanglements. It's kind of a similar kind of entanglement, and it's also kind of the magic that makes AI work, right? It's these probability distributions over many factors. So what happens here? I mean, how is it that just the fact that the warden said something can affect the chances of another prisoner surviving, right? Well, it's counterintuitive in a sense, but what happened is we've collapsed some part of this joint probability distribution, and that's where we ended up in. So that's this is a kind of a magical thing about probability theory, right? That this is how joint probability distributions work. So probability distributions are multiple factors, and how they entangle these different factors, and I think that's where a lot of the stuff that we find very counterintuitive sometimes. That's why these puzzles are so cute, right? Because we find them counterintuitive because we're naturally not that good at reasoning about collapsing joint probability distributions. Yeah. Actually, now that I think about it, I could have made this a lot simpler, right? So I could have got rid of the pardon box totally, and I could have just discarded here. It would have been the same subprobability. It would have been the same distribution, right? So it's just this thing here just collapses this joint probability distribution. That's this kind of almost like action at a distance, right? It's this. It seems like magic, but it's. Yes, exactly. Yeah. This is this kind of a notion of entangled joint probability distribution. Just like in quantum, when you measure if you entangle two qubits and you measure one, that has an effect on the other. So it's very similar. Any other questions? Okay, in that case, this is actually where I wanted to stop. So I didn't really prepare anything more. So I just have a conclusion slide and we can have an early lunch. So conclusions. We played with string diagrams for modeling probabilistic puzzles. So this is somehow the state that I'm at right now. So I showed you, I said at the start that I'm starting now this project of thinking about developing probabilistic logics for AI, for safe AI systems. So I want to extend these kinds of probabilistic applications of string diagrams. And I also I've been working for many years on understanding how to reason logically with string diagrams. So string diagrams are very good at capturing various kinds of formal logic. So I actually cited a paper that I wrote with some of my colleagues that we presented at LIX this year about how to do first order logic with string diagrams. So I want to kind of combine this probabilistic understanding of string diagrams with the logical to develop something like probabilistic logics, and I think that's going to keep me busy for the next few years. But there's a lot of probability theory relevant for AI, right? So what I didn't talk about is this notion of updates, belief updates, right? So this is really at the center of artificial intelligence, right? So if you have a prior distribution and you make an observation, then you want to update your distribution. You want to update your understanding of the world to fit your observations. Okay, and this is really the process of learning in a very abstract sense. So, as you feed more data, you become better at understanding the probability distribution, this joint probability distribution over the sample space. And there's a lot of, fundamentally, this is how all learning algorithms work. I mean, there's different technical ways of making these calculations, things like gradient descent, backpropagations, etc. Also, what I didn't talk about is Bayesian reasoning and causal inference, which are very important parts of probability theory with really deep applications in computer science. So I want to work more on these things, also using this kind of algebraic approach that I showed you. And what I didn't touch on at all is things like probabilistic model checking, which is a very advanced part of computer science, where you really have probabilistic transition systems and you want to verify the behavior, and the verification will produce you, things that you can be certain with a certain probability, right? So it's very a probabilistic setting, and also probabilistic programming. So there's a lot of work in the recent years on probabilistic programming languages. And in fact, at Marcos University in October, there will be there'll be a school, I guess not a summer school, because it's some kind of almost winter school in probability theory and computer science. Autumn school, yes. Well, October in Denmark, it's already getting a bit cold. Okay, so thank you so much. Thank you for your attention. It's been a lot of fun. You're a really great cohort of students. So it's been great. Thank you.
So thank you, Pavel, for the nice presentation. It's very interesting for us in computer science. Recuerden que esta tarde tenemos otra jornada. Lo esperamos a partir de las 2 y estaremos hasta las 4, ¿cierto? Ahí se hará el cierre 4:30. ¿Cómo está? De estudiantes. ¿Listo? Entonces esperamos por la tarde. Ok. Y Marco será el presentador esta tarde. ¿Listo? Bueno, vemos en un rato entonces, muchachos. Gracias por la asistencia.
segunda sección tenemos por el profesor Marco, que va a seguir con su segunda parte de A Gentle Introduction to Session Types. Y luego la sesión de los estudiantes, que todos están invitados también para que sepan los estudiantes un poquito mayorcitos que ustedes que están haciendo en el proyecto Promueva, que es el proyecto que yo dirijo aquí.
All right. Thank you, Frank, and welcome back. I hope you're not too tired after lunch. After power? No. Right. So let's see. So yesterday we have been looking at the first two parts. One was I showed you this. We tried to go through the semantics of this toy language, which I call toy Erlang. And so we have seen how you can program some simple things, like this customer shop and logger example. And then we moved to the second part where I told you, okay, can we just write a protocol language where we can abstractly kind of describe the sequence of interactions that we want our program to follow when we execute it. And I'll try to, we looked at these choreographies. So if you look, this was for the choreography that describes the protocol abstractly, the protocol that our customer shop logger example has to do. And if you remember, we had, so it started with the customer making a choice, communicating a choice to the shop, and the choice can either be price, buy, or reset. And depending on which choice the customer chooses, then the system, what the choreography says that the system has to continue according to the corresponding sub protocol, right? So here, for example, the shop, if the customer chooses shop, then the shop has to send a string to the logger, and then the shop sends an integer to the customer. And then the T is just for doing recursion and repeating it again. That's the kind of protocol we're modeling here. In the case of the buy, the customer sends its credit card. This is a credit card type, whatever that is, to the shop, and then the shopper logs with a string. And we have the third case where the customer is not involved. Of course, the customer should choose this reset. So it communicates, but then it stops. And it goes back here while the shop and the logger communicate. Now, what we saw was this notion of projection. So this is the syntax of all these choreographies. And the notion of projection, now I'm not going to go through the formal definition, but I'll just put the example here. And I think this was maybe not very clear. So the choreography here, and here I have the projection of this choreography. What does it really mean is that here the choreography is giving me a global description of the global protocol. It's telling me how the whole system has to be executed. What is the protocol that the system has to follow? While the projection is kind of local, it's basically a local view of what the choreography say with respect to one particular actor. For example, if I give you this choreography here, and I'll tell you what is the local view with respect to the customer. Okay, then what you do is that you just look at this choreography here, and you can see that there are points where the customer is not involved. However, there are other parts of the protocol where the customer is actually doing something. And the projection is going to extract from the global protocol, is going to extract the behavior of that particular actor that you are projecting. So for example, in the case of the customer is making a choice among these choices here. So this one means send, make a choice and communicate it to the shop. Vice versa, if we look at the shop, is doing the opposite thing. In fact, it's expecting to receive something from the customer. And what is expecting to receive, here we're being precise, is either expecting to receive the price, to receive buy, or to receive the reset request label, whatever you want to call it. Okay? So really a projection is looking at the global type, at the choreography, and extracting the behavior of one particular actor, the actor that you're willing to project. So if I tell you, in that thing up there, what is the logger doing? Well, the logger is something in a loop that is always expecting a message from the shop, because in all branches is behaving like that. Now, this generation here, you can do it automatically. You can define an algorithm that, given some syntax like that, it automatically generates one of these guys, given also an actor. And what we did yesterday, was to define this, and it was this projection, proj, whatever you're going to call it, PRJ, that basically says, well, if I have a global type, a choreography, I said I would call them, I would interchange the names, like this, and you are projecting some actor P, then the definition says that, well, if what you are projecting P is actually this P1 here, first case, then you need to do an output. If what you're projecting is this guy here, then you need to do an input. If it's none of them, then you just continue projecting the continuation. Okay? Is that clear? So one thing that I would like to mention, maybe briefly, is that I told you a little bit about the projection of recursion, where you have to be a little bit careful because you want to avoid to generate this stuff here. But then there was a really important thing that I mentioned was about the projection of branching. And the whole point was that when you project branching, you know that these two guys, so P1 is going to make a decision and select one particular branch here. And this decision is going to be communicated to the receiver, to P2. So after this branching is executed, so actually the program executes this branching operation, so which means this guy makes a choice and sends the label to this one receives it and know which branch was selected. The only actors that know which branch was selected are P1 and P2. No one else knows that. And now the question is, since I have many branches here, and in these many branches, I could have other actors being part of the protocol, the question is, who tells them which branch was selected? For example, here, customer and shop, they take a branch. However, the logger needs to know which branch was selected. I mean, somebody has to communicate this piece of information to the logger. And what we did in this projection here, which is the most standard way of projecting in the literature, is to say, well, actually, we don't want to worry about that. And we just put a restriction that requires that the behavior of any actor that is not part of this branching is the same on all branches. And this one works because the logger is doing exactly the same thing in all branches. It's always receiving a string from the shop. And its projection can be simply written like this. Now, is this clear? I mean, ask me if you have questions. Now, the point is that, I'm sorry, I forgot to put the colors there, but yeah. actually, about 2 years ago, with my PhD student, we were. I will tell you a bit more about this later. But we try to actually formalize all this theory here. So into a proof assistant. I don't know if you ever heard about COC proof assistant. So it's a program where you can define mathematical things, and then you can actually prove theorems about them. And the advantage is that, assuming that the implementation of COC is correct, and I think it is, well, statistically it is. There's not many bugs being found. I'm sure they still find bugs, but if we trust COC, then you're sure that if you manage to prove something there, that your proof is correct. Now, I don't know what you do when you do exercises or when you do exams, but it happened to me many times that I was sure of answering correctly all the math, but maybe I forgot a plus or a minus somewhere, and what I got was wrong. Has it ever happened to you? It happened to me all the time, unfortunately. But and the point is that when you do these proofs, so here, for instance, you would like to show that the projection I showed you is a correct operation. It's an algorithm that generates a local type out of a global type, out of a choreography. And there is a proof. And I will give you a hint of how basically we do this a bit later, but what does it mean? I mean, is it correct when I do it on paper? And actually, in this project where we mechanized the whole theory of session types, actually, of multi-party session types, we found out so many bugs that they were on paper before, that were overlooked. I mean, mostly small things, but it's really easy to overlook these things. And then basically what happened is that while we were playing with this, we found out a very strange inconsistency in the way the projection is defined. And here is an example. So here I have a global type, choreography. I don't know why I say global type. Maybe I should just call it global type. But anyway, and what happens is that, I mean, it's very simple what happens. So there are 4 actors, and Alice sends a string to Bob, okay? Then Carl makes a choice, go left or right, and communicates that to Dave. And then if left is selected, then you go back to the starting point here. However, if right is selected, Alice has to send a string to Bob, and then instead of going back to the starting point, you go back to this point here, T prime, okay? So basically, if you imagine to execute an implementation of this protocol, what happens is that basically Alice continuously sends a string to Bob, no matter which branch Carl and Dave take, because if they take this branch, then the protocol will force me to do an Alice to Bob first. And if they take this branch, they will do an Alice to, there must be an Alice to Bob first, and then go to this point again. While Carl and Dave, they just branch, they just make a choice at every iteration, okay? So they are sort of independent, what Alice and Bob do from what Carl and Dave do. Now the question is, what is the projection of Alice? And if you're projecting Alice, you'll see here that, well, there will be an output of a string to Bob. However, when we look at the projection of Alice on these 2 branches, and Alice is not involved in this branching here, we see that on this branch here, we get a T, a recursion variable, because that's the way the projection is defined. While on this branch here, we get an output dot, followed by another recursion variable. And now, since the condition on projection says that the projection of Alice has to be the same on both branches, the projection fails, and basically this choreography here is not projectable for Alice. I mean, it sounds a bit stupid, but that's the way the definition. And actually what we did, this is not wrong, it's just saying we are rejecting this choreography here. We cannot process it, it's fine. However, what we found out, we started looking at a lot of papers in the last 10 years, and nothing was wrong, but then we looked at the examples they had. And lots of the examples they had didn't project because they had a problem like this. And now I'm going to tell you this other example here. It's slightly different, syntactically at least. And what it says, look, Alice writes to Bob a string, Carl writes to Dave and makes a choice, left or right, and then in both cases, you go back here. Can you see that these two protocols are basically the same thing? I mean, in that one, Alice is continually sending a string to Bob. And then independently, Carl is making a selection or a branch. And here, it's happening exactly the same thing. Actually, if you can imagine this one is recursion. So if you ever heard about unfolding, what you do is that if you see a recursion like this, you take the whole remaining term and you substitute it for every occurrence of t. And if you do this infinitely, you will get an infinite tree. And basically what happens is that the infinite tree that you get from here is the same as the infinite tree you get from there. And basically what it means is that the infinite tree representation of these two global types, which are syntactically different, using this recursion here, is the same. So somehow this tells us, well, maybe these two global types are equivalent. However, if I try to project Alice here it's projectable, because here I get, it's an output of a string to Bob, here it is, and then the projection on the two branches of Alice is the same, it's t and t. The side condition is met, so actually Alice is projectable here, but it's not there. However, they are equivalent, basically, choreographies. Yes?
So like the way you write these types, it looks like Alice has to send a message to Bob, then Carl to Dave, so they have to alternate, but there is no communication here, right? These messages are completely independent. So why write it like this? Why the dots?
Yeah. I haven't. So I could do it. I have the slides, but I don't know if we have time for that. Both global and local types, so choreographies and local types, they have a semantics. So you can actually define a semantics, where basically you can observe whatever can happen next. In a global type like this, since there is no dependence between this interaction here and this interaction here, because it's four different guys that, I mean, the first two talk to each other, the other two talk to each other. Actually, the semantics will tell you that you can either do that first or this first. And this is because you can swap them. So actually, we have an equivalence relation on global types that allows you to make these sorts of swaps. So why would I write the global type like that when I meant something like this? I fully agree with you, I wouldn't. However, it is syntactically possible. They have the same coinductive representation, so the infinite tree, therefore something is not working there. So this is just an example.
So you're saying they're equivalent because if you like see them as a tree, they are the same tree.
Two reasons. Intuitively, if I look at the behavior of each actor there, it's the same. on both cases. I mean, what is Alice doing? Is continuously sending a message to Bob. And what is Alice doing here in the clean version is continuously sending a message to Bob.
So do you have an algebraic way to, let's say, cancel that right branch there that seems unnecessary, or?
No, because this is not, it is necessary because you're doing two different communications here. One is left and the other one is right. So they are distinguished. It's just that, I mean, if you imagine to unfold this, then it's true, yes, that you will have the same term here when you unfold. But it doesn't necessarily have to be like that. I could have Carl and Dave doing something here and doing nothing here. But then I would have to change that one as well. So this is just a counterexample, okay? Maybe it's not fully meaningful from a practical point of view. But it was mostly an observation about the fact that basically the projection of these recursive types is not complete with respect to the infinite tree representation. And basically what we found in this paper, we defined a projection on the co-inductive version, so on the infinite tree representation of these global types. And then we defined a new projection for these types that is actually complete. And the way you do it is a little bit more complicated. I have an example. I will show you actually how we project this. There was a question there, maybe, or yeah. Frank, can you? Yeah.
Okay, so I just want to make sure the one that is deciding, like making the decision, is Carl, and he's communicating that to Dave.
Yeah.
Oh,
Yes.
okay. Okay, yeah, that's it.
I mean, about the branching only. But Carl and Dave have no idea that Alice is sending a string to Bob. Of course, you see it here because this is the choreography and you're supposed to see everything. But when I project locally and I look at the behavior of Carl and Dave, what these two guys are doing is irrelevant. Yeah? It's easier like this.
Okay, so if it really doesn't matter if Carl is communicating to Dave left or right, is there a way to just simply ignore that communication and do it anyways, without caring about the message that Carl is sending to Dave, like a default option? Carl is communicating to Dave, and no, yeah, there, left or right. And in the two options, it goes back to the start. So there's no way to do a default route, like anything that Carl communicates to Dave goes to the same point, T?
Right. So if I understood correct, the question is like, in these cases, you are going back to the same point.
Yeah.
And could you just write it in a different way? Yeah, you could just write one branch only, and then you just go back. It would be a different protocol because, I mean, here we are kind of observing anything that happens. So here there is a communication of a left, and here there's a communication of a right. So it's a different message that is being communicated. I mean, in an implementation, this could be relevant, for example, because it could be, if I receive a left, I record the time. If I receive a right, I don't. And you don't see that because here we only care about the communication. So we don't know what happens locally in every actor. So don't forget that the types are an abstraction. So you forget some details that they are not relevant for the communication patterns again, but they could be relevant for what you compute. Right, so I will run a little bit fast here. Maybe I won't tell you what the problem is exactly, because otherwise we don't have time to look at the rest. But we did define a different projection. And the way this projection works is that if you remember in the projection I showed you before, you just projected the first branch, and then you had a side condition that checked that all branches were projected the same, right? You just choose the first one, but they're all the same. Instead here, what we do is just we project all branches. So I project all branches, and then I return a set of projections. So the way you can imagine this is that if you look at a choreography and it has many branches, so if you look at, it's like a tree, right? And you can imagine that each path in the tree is one sequence of interactions. And then what we do is we project every path in the tree. Okay? So if I project every path in the tree, I will collect, for some role, I will collect a set of local types, basically, or projections. Okay? Because you're creating a set here.
Yeah, but the type, I mean, the other two are not sets, right? Yeah.
It's a string of where you collect. Okay, it's a bit of abuse of notation here, but what I didn't tell you is that I've defined some syntax for this. So it's no longer a global type what you are doing here, what you're a local type what you're generating here, but you are generating. In the end, you will get a set of local types, and it's a syntactic thing, but you can actually do it not syntactically. So I'm a bit hand waving here, but you can define this precisely. But I mean, I think the most important thing is the intuition that when I do the projection, what I do, I will get a set of local types. And then all you have to do is to check that they are equivalent up to unfolding. So basically this relation here, which I define here, and you don't need to look at this, is basically going to check that the infinite unfolding, so the infinite tree corresponding to each of these local types are all the same. And for those who know coinductive definition, basically what you do there, this is a coinductive definition defined here, and it's decidable because this stuff is regular. It's a regular language. So I won't tell you more about this, but you trust me. So with a counter example, for example, what you do is that you have two paths, okay? And if we project Alice in the left path, we will have an output of this would be a string, I'm sorry. Okay, but yeah, output of a string plus this, which we can discard. It's just a t because this one is not being used at all. And in the lower path, in the right path, again, you have an output of a string and again, an output of a string. So basically you have, let me just write it in a simpler way. In the top, you get basically mu t output of an int dot t, and at the bottom, you get mu t string, sorry, output of a string dot output of a string dot t. And basically, that relation that I showed you in the previous slide here will tell me that these two guys are the same. I mean, can you see they're the same? I mean, it's continuously send, but it's just written in a different way. And basically, because of this, we do this check, and then we can say that it's projectable. And then you can choose for the projection either, because they are equivalent. All right. One last thing that I mentioned, but I'm not going to go through the details because I want to show you a little bit about, there are two things that I really care about now showing you. How do you use this global and local type to check that toy Erlang programs are well typed, are correct? And then I want to talk to you a bit about what kind of work we are doing right now, what kind of research that you may be interested in. So I will skip this part. Yes. So, and we move to part 3 here. How do you use session types to verify these concurrent programs? And if you remember, I had talked about types as a basic ingredient, right? For basic concept for guaranteeing basic properties. And so what we are going to do is that basically we are going to use these types, these choreographies and their projection basically to type the communications that these Erlang programs do. And looking at the whole picture, so this is my Erlang system. So I have some code for each actor, and then I have the global types. The general methodology is that you do the projection, and then you generate local types, and then you use the local types to verify the code. And the result that you want to have is that if this works, if this passes the check, then you are sure that your programs, when you execute them, they will follow the protocol specification. So how do you do that? Have you ever seen a type checker? Have you ever implemented a type checker for some standard programming language? Actually, this is something that you do when you do compilers as well. And the idea, the way we do it is very similar. So what you do is that you basically have to write an algorithm, like a function that you execute, and you give it as an input your programs, and it runs through the program, and it verifies that it follows the types, basically. So you can look at it as also as a function that, given some expression in the Erlang, from Erlang, and some local type, it will tell you true or false. So it will tell you whether that expression is typed by this local type you give it or not. So the way I've written it, you can look at it as a predicate. And in math, you usually write it like this. Of course, when you implement it, you will implement it a function. But I'm going to write it like this because it should be hopefully more intuitive. And basically what you do is that you say that you write something like this. So you have some expression in toy Erlang E, okay? And this thing is saying, this mathematical object here is saying, well, the expression E is of type U, so it could be an integer or whatever, a bool, or a function type. And it says from a session type, from a protocol point of view, it says that before I evaluate the expression E, the protocol tells me that I have to do this. And after I evaluate the expression E, the protocol will become something T2. So, and this is extra, forget about this for now. So just to give you an example, I could write something like this. I have an expression here in Erlang. I think this 2 is a mistake, shouldn't be there. And this one is just saying this expression, send number 4 to actor P, okay? Now in Erlang, when you write something like this, it will return, after you execute this, it will return you the value that you're sending, also locally. So this is an integer. And what is the local type? Well, the local type, for example, this is just an example, it could tell me that first I need to send an integer to P, then I have to send another integer to P, and then terminate. Well, after I execute this guy, first I need to check that, well, the first thing I can do if I do input-output operations or send and receives, I have to send an integer. Precisely this expression here is sending an integer. So I will match that, take this out, and after I evaluate this, I will be left with this part here, which is what I have here. Okay? So this is just an example. Now, I want to define a general algorithm, right? Or a set of rules, this is actually what I'm going to do, that given any expression, it will check that this thing here is satisfied for any T1 and any T2. So, are you ready? So these are the rules for the very simple language that I showed you. Okay, this is scary. Which one is more scary? It may seem a little bit complicated, but actually it's not. And this is a very simple system. But just let me say one very important thing here. With these very simple rules, if I have to prove some correctness theorem based on these rules, it will be at least 20 pages. So how likely it is that I will make a mistake? Very likely. So that's actually just to sponsor more. Please, if you can, try to mechanize your proofs in a proof assistant like Coq or Isabel, if you know that. Anyway, I'm not going to go through all the rules, but I want to show you the most interesting ones. Okay, so I have them all here, but I will let's start basics. So if my expression is a constant, okay, here there is no effect on the local on the session, on the protocol. Okay, so T shouldn't change. Do you agree? This is just a constant. So it could be a number or it could be a Boolean. So the only thing I want to check is that C is actually of type U and some other system that I'm not defining. And in this case, if I have a variable, basically I only want to check that my variable is in my extra environment because I need to remember that. It doesn't matter. We will see this later, but yeah. Now, I will skip recursion, but we will look first of all at function application. So function application is just uses a standard typing rules that, for those of you who have you ever heard about the lambda calculus? And so there is a very simple typing system for the lambda calculus, so they simply type lambda calculus. And the rule is roughly this one. Here I've added just some extra things, but basically it says, wait a minute, if I'm applying E1 to E2, so E1 has to be a function from U1 to U2, this is the type, and if E2 is of type U1, and I apply the function, I will get something of type U2, okay? So this is simple, this is very basic. There is a little bit extra thing, is that when we evaluate these expressions here, we could have side effects. What are the side effects? I could do send and receive, so I could change the protocol. So the way we evaluate these expressions when it's function application, I've chosen the following order. First, you evaluate E2, and then you evaluate E1. So first, we evaluate E2. So starting from protocol T1, I get to some T3, then I evaluate E1, but then I have to start, so this may have done some sends and receives, so the protocol may have changed. So when I start evaluating E1, I will have a different protocol, T3. And then here I will get T2. And T2 is here. The last piece of information is this thing here. That one we needed for recursion. If you want, I can tell you offline a bit more about this if you're interested, but we don't have time to go into details. Yeah, I'm annotating types also with these local types. So basically, this is a function that when I evaluate it, it changes from T3 to T2. So, okay, I haven't shown the rule here, but I'm going to use it here, basically. And here. Then I will have to use it here as well. But let's skip it. We don't have time for this. Sequencing. It's even more simple. Here we don't have all this function application and thing, but it's the same principle. First I evaluate E1, then I evaluate E2. So if my session starts from, says T1, sorry, my protocol, and then I evaluate T1, I get into T3, then I evaluate T2, from T3 I get to T2 here, and I get this one, okay? Conditional, it's a little bit more simple. Basically, you want to check E1. It may change the protocol, because here I could do send and receives, but here I'm forcing E1 to be of bool type, because it's a guard. And E2 and E3 have to have the same type, and they have to have the same effect on the protocol. This is because eventually they need to take you to the same place. In most cases, when you do this kind of typing, this guy is end, because the protocol execution will be continued inside here or inside here. So eventually you terminate here, unless you have some recursive things. Okay, here's where I wanted to get. So the interesting ones. What do the interesting ones say? So this one is saying, I have an output, okay? I'm sending the evaluation of some expression E over to P. And this is going to be of type U. So that means that E also has to be of type U. And then the session, the protocol. So T1 is how the protocol looks before I start doing anything. However, before doing this send, I need to evaluate E first, right? And E may do other sends and receives. So the only thing that I require here is that what I get after evaluating E, something of this type, where there is first an output, and then there is T2. Because then this output is going to match this output, and then after I execute this output, I will be left with T2. The receive is basically the same, inverted. The only thing is that I don't have to evaluate before executing the receive anything. So I can immediately require that the next thing that I can do is an input, which matches this receive, which is basically the type of the object that I receive. And then after I do the receive, I need to type E. So I start from this T1 here, and I will get to some T2, which is going to be what I'm left after I execute the whole thing. I'm not evaluating anything. This is static. But what I'm saying is that I need to imagine that I have a protocol, and after I evaluate all this thing, how will the protocol look? I'm not going to evaluate it. I need to predict it statically. And basically what I know is that what I get here is the protocol that I'm left with after I process also this E here. So not only the receive, but also have to do the E as well. If you remember, the semantics says receive, and then X will be the value, it will be passed to E. So, and what I'm left here is what I'm left from here. And then here you can see that the X is saved here. So because this is static, in E I may find this X, and its type is given here in this environment here. Okay. Should we have a break? Yeah.
Receso 15 minutos.
All right. You're standing. All right. So let's continue. Yeah, I showed you how to do the typing of the output of the send and then the receive. Similarly, you do it for the selection. So instead of sending an expression, you send a label, if you remember, in the language. And this is much easier because then you just require that before doing the send, your protocol looks like this. Namely, you are selecting a label and sending it to P. And this is what we're doing here. And the only check that you're going to do is that the label that you're sending here in the syntax in the program is one of the labels that are in the type. Let's check here. Why? Because if you think of the projection, if we start from a global type, from a choreography, it will generate something like this for one actor, and then it will generate something with the ampersand here for the other side, for the receiver side. And what we want to make sure is that when I send this label, then the opposite operation will be offering that option. So if I tell you, let's go left, but the receive doesn't have a left, it only has a right and right, then we would get stuck. So in here, what we're checking is that, yeah. Where? Oh, yeah, this is TI. I'm sorry. Yeah, thank you. Yeah, sorry. And in fact, the receive, yeah, here you have TI indeed. The receive, here what we check is that all the branches we offer are also in the type. Okay? And then the receive, each branch has a follow-up expression that you need to evaluate. So each of them need to be evaluated. How do they change the session, the protocol? Well, after I do the receive, depending on the branch I take, I will start from a TI. Then I will evaluate the EI, the corresponding expression. So this is like set notation. Sorry if I use this. I didn't want to write it very long. But then all of them, they have to end in the same T. And usually this one you can imagine is an end, unless it's recursive things. Right. So what you could do is to take the local type for the customer, take the code for the customer, apply those rules, and construct a proof that actually this local type types this guy. Actually, before you evaluate this expression, you will have this local type, and after you will also have this local type because it's recursive. Okay. And the whole point is that you go step by step, right? First, there is a selection of price, buys, and resets, and you see it here. Oh, price, good. I have this. I can discard all these other ones because I'm not using them. And then you look at this. Okay, price, it must receive an integer from the shop. Yeah, indeed. It receives some Y from the shop. And then you go on, okay? And yeah, here there is recursion, so you will have to unfold it a few times, this thing. Okay? So what is the state of this? So this type system that you've seen and this language that you've seen, I have written it last week for preparing these lectures. However, we are actually working on this on a more general version. So actually almost the whole Erlang. And we are implementing it. But this is still ongoing progress, ongoing work. Sorry, work in progress. Just one more piece of information. If you remember, I have many actors, and each actor is executing some expression. So actually, what you can do is that you have some global type, some choreography G, and if you have a whole network, so the whole actor system, then you can say that this is typed by some global type slash choreography G, and after I execute it, I get to some G prime if each of these guys is typed by the projection. So I project every single one, and then I get that for some UI that you can guess or give it in advance. It's the gamma that I had for keeping the variables, and in the beginning is empty. So it just means empty, but then when you start typing these guys here, you will start adding stuff when you have binders, basically. And I had promised Frank I would mention subject reduction, but I'm sorry, I couldn't. So actually, you can prove the following theorems. I haven't proven it actually for this system that I've given you, because I didn't have the time, but we have proven it for the more general setting. And this sort of theory is something that has been going on for many years now. So the first theorem, which when you write a type system, that's the most important thing that you need to prove, because it shows that the type system is actually correct. And basically saying, well, assume you have some network N, so a set of an actor system with many actors, and assume that you can type it with some global type choreography G, okay? And you get into G prime. Then basically what the subject reduction is saying is that if you start evaluating your expressions, you do steps of reduction. You remember the semantics that we saw yesterday. Then what you reduce to step by step is still well typed by some G double prime. And actually, you can say more. The G double prime that you get here is, I haven't shown you the semantics of choreographies, but basically it's one step of evaluation that you can also do it in the choreography. And these alpha, basically they say which communication has occurred. I'm making it a little bit more imprecise here, but the basic notion is that if your network, you start evaluating your network, then your network keeps on being well typed, to be typed by some choreography. And this is important because it means that whatever you can reach, whatever state your system reaches, still is well typed. The second thing is that, if you remember, I told you these choreographies are somehow deadlock free. So all these protocols that they guarantee, they are free of deadlock. In the system, I've shown you, actually, if this is well typed, then it actually is deadlock free. So you will never get stuck. Okay, so you will either always reduce because you have some infinite behavior, or you will terminate. Okay? So this is a property that session types give you, and it comes from the choreographies. And then the last thing, which is also very important, that's why we define a type system in the first place, is to what kind of basic properties do we want to guarantee. And actually, this theorem tells you that if your system is well typed, then you never have a communication error. Which means it's never the case that I send you a label and instead you are ready to receive a Boolean. Or I send you an integer and you're expecting a bool. And that will also transfer to the functional part of the language. You will never apply a function from int to bool to a bool, for example, because a function from int to bool expects a bool, an int first. Yes, Frank?
So one of the students was asking if there was a notion He's studying the studying subsystem for logic, so he's wondering if there is a corresponding notion of completeness or soundness or categorization for these subsystems.
Right. So I actually have a slide later on this, but so what I can say is that so there is usually so if you take the simply typed lambda calculus, and there is a Curry-Howard correspondence is called between logics and the type system for the lambda calculus. And that means that you can look at types as formulas in the logic. You can look at reductions in the lambda calculus while you evaluate these expressions as proof transformations, actually cut reductions. So cut in the lambda calculus is, if you know what cut is in logic, in the lambda calculus will be functional application. Here is a little bit more complicated. We don't have cut elimination. So cut should be parallel composition if you want. Is a little bit more complex because you are composing many actors, not two. So this kind of analogy or correspondence, if you want, between session types in general and logic, actually it's linear logic in this case, has been studied a lot since 2010. I've also been working a lot on this. And there are restrictions that you can put so that you actually have some sort of results and similar behavior as you would have in linear logic. So you would have cut elimination, so that would correspond to strong normalization in the system here. So, but you always have to terminate and so on and so forth. Okay. Right. Yeah, just to, if you want some references, I basically based all the typing theory and all the things that I've shown you so far on this work here. So the first one is the first paper ever on session types. This is the work on multi-party session types that we were also mentioning yesterday. So it was the first one that introduced these choreography global type things with local types and projection. In the first one is just binary. So you only have these protocols only between two parties. And then I've used a little bit for the functional part, this work here, and also this one, which has just come out, but it's not been published. It's just available online. And I'm not the reviewer, just in case. I don't even know if they submitted somewhere. And then all the story about the projection and that case where you had this one global type, one choreography was projectable, the other one was not, is this work here from last year. Yeah, right. So let me just do the last part now. Do you have any questions so far? No. All right, the last part. The first thing is this gainer project. So that was maybe what you also read in my abstract. And the idea is to do, as I've shown you, basically, to do session types, multi-party session types for Erlang. There is more that we want to do, that we are doing. We're working on it, but still we don't have a lot yet. So one thing is to make this thing gradual, and I'll tell you in a minute what it means. And the other one is to reason about information flow. So have you ever heard about gradual typing? So the point is that you have two types of typing. There is static typing, like the one I showed you. I give you the program, I give you some types, and before even compilation, you check statically once that your program is well typed. And then what the guarantee you have is that when you run, some property will be guaranteed. That's the first version. Then there is the second version, which is more dynamic typing, which is more like the use of monitors. And that's the way actually Python, also Erlang work. So that means that there's nothing you do statically, you just execute your program, and at some point, you may catch an error at runtime, and what you do is you kind of install handler that handle the error, for example. It's like usually working with exceptions, for example, in some programming languages. And then this guy here, these two guys, Siek and Tahan, many years ago, I think that's the earliest paper I could find, they proposed actually gradual typing. And the idea of gradual typing is, okay, wait a second. First, what is the advantage? So the advantage of static typing is that you check once your program before you compile it. Then when you run it, you're sure that it works. Dynamic typing is you don't know in advance because you cannot predict things. And you hope that at a runtime, you will have some monitors or handlers that will catch these errors. So very different approaches. However, the disadvantage of static typing is that it's heavy for programmers. Why do many people like to program in Python? It's because you don't have types, so you don't have to go and bother, okay, this is of this type, or now the compiler doesn't let me write it because it doesn't type check. Especially, I don't know if you've worked with Haskell. Frank told me that you're working with Haskell. In Haskell, you really have to fight sometimes to make it work. On the other hand, if you use dynamic typing, it's fantastic because you don't have to worry about these things, and you have much more flexibility. Now, the point is that these guys here, the second paper, Igarashi et al., that includes also Philip Wadler, if you know him, they have said, actually, they've looked into session types and actually looked into gradual type for session types. And what they found out actually is that you can also have advantages if you go with something typed, non-typed, instead of something strongly typed. Now here I have two examples of a server in their language. But basically what this thing is saying is that this is basically some protocol, some channel where I'm accepting messages to like reading my mailbox. And what it does is that the client will send you a message and it will select a label, right? And this is the operation that the server is providing. Either negate or add. If it's selecting negation, then what you do is that you receive some integer, and then you negate it and send it back. Okay? If instead it selects add, what you do is you need to receive two integers, add them up, and then send it back. Okay? So this is an adder, this is a negation. And the difference here is that in the first case, I receive only one integer. In the second case, I need to receive two integers before giving the answer back to the client. And this one, you can type it with session types because you have a branching here. You know, it's the ampersand that I showed. It's either negation or add. And then here there will be one input, sorry, and here two inputs followed by an output. So you can do it like that. However, they say, okay, this is cool. You can write this. But now imagine that I want to make my compute server more flexible and open to adding new functionalities. Now, if I do that, then every time I add a new functionality, I need to define new code. And now, if you look, there are two differences between these two operations here. One is the actual function that you compute. Okay, this is like a function, just a function. That one, of course, you need to define it every time you define a new functionality. However, the only other difference between these two functionalities is that one receives one argument for the function. The other one receives two arguments for the function. And now they say, well, assume I want to define my server in a totally different way. I want this to, here, it provides all the functionalities that I want. I have them here. And the functionality is defined as follows. The number of parameters that I need to input. So in the case of negation is only 1. In the case of add is 2. And then the functions that computes it. And actually, then I want to define this once and for all. So I could define also another argument, another operation here that takes 3 inputs, 3 values that needs to input from the client. So basically, I want to make it parametric. And then here, what this function does, we don't need to go into detail, but it receives n times first, and then finally it sends the result of the function that you pass to it. Sorry, this up here. Okay, so it's a bit smarter way of coding this. Okay, and it could be an advantage. Yeah. No. Now the point is that the bad news is that there's no way you design a standard session type system for typing this thing. You cannot do it. And the reason is that in order to do this, you need a much more powerful typing discipline. So you need dependent types. You wouldn't be able to do this in Haskell either. You would need to do it in IDRIS, for example. So you need a much stronger type system on top of that. And basically their argument is that, okay, cool. So can we actually have some flexibility and have some parts of the code for which we do not specify the type, and other parts of the code where we actually specify the code, the type. And this is basically gradual types. And what we're doing, we are trying to introduce this into Erlang. Some people from WhatsApp, they've already actually done this, not for session types, but for standard types. So they have designed a type system that is gradual for Erlang, and this is open source. You can download it and use it. Where basically you can code in Erlang, use types, and sometimes you don't have to use types basically. So you can use both worlds in one thing. And then the second part is what we are trying to do is to add into Erlang again this idea of non-interference. And what you do is that, I mean, non-interference is basically you care about information flows in the system. So, and then what you can do is to look at the choreography of the system and somehow label the data that you transfer from one point to another with some security level. So for instance, here they are using 2 levels, bottom, so it means it's not secret, and top means it's secret. And then what you can do is there is actually this paper here from 2010 actually, where they use this kind of specifications, and then they are able to tell whether if this is typing some code, then they're able to tell you if the code does information leak, which means some secret information is going to be transferred to, is going to influence the communication of non-secret information. We don't know yet how this can be transferred into Erlang, and we have a student actually working on this. Yeah, what we have done so far is that we actually defined the type system for Erlang using GenServer, which is a sort of library that allows you to do some remote procedure calls. we have extended it actually to gradual session types as well. Currently, we're only supporting binary protocols, and we have implemented it. We are implementing it. One more thing, I was talking before about mechanizing proofs. What we did was this project actually was funded by the Independent Research Fund Denmark. And its goal was to just take this paper from 2008. Well, this is the 2016 version with all the proofs, 100 pages. And say, okay, can we take this all these theorems and so it's a theory of multi-party session types, like the one I showed you, a little bit more complex. And the question was, can we mechanize it in a proof assistant like COC, and actually verify that all the proofs in this 100-page paper are correct? So COC is an interactive theorem prover. Have you ever heard about it? No? Some of you not. But it's just imagine some tool where you can write definitions, theorem, and then you start writing the proof, and then it will check that your steps in the proofs are correct. It's very useful, and you should do that. You should use it. So yeah, this is why we wanted to do it. Well, it actually was very surprising. Well, was not very surprising, perhaps. We found actually a lot of problems. First of all, a lot of details were missing. So when you mechanize it in a proof assistant, you will end up looking at the details. You also have to define that if 2 is equal to x, then x is equal to 2 as well. You will need to define all these small things. And when you do that, a lot of new things will pop up that you didn't expect. But in particular, actually, we looked at the subject theorem of the paper, and we found some imprecision that is incorrect. And what we did, we actually fixed it. And we have a new system, basically, that now works. And also the problem with the projection that I was telling you before, it came out also out of this project and of this mechanization. So, and the question is, okay, the authors, including me, of that paper, were we so lousy that we didn't do the right proofs? We were really bad at writing proofs? Or is there something else? I mean, I'm talking about 100-page papers. And I mean, I'm not showing you what the issues are there, but they're easy to understand. However, I think it's very unlikely that you could have caught those details that invalidate the theorem, unless you mechanize that. And also, I mean, it has doesn't mean that we should mechanize in a proof assistant everything. Yeah, perhaps, but it's not easy. I mean, basically, this project has lasted 3 years. So that was really a lot of work to mechanize. We have like over 20,000 lines of code to mechanize the whole theory. Yeah, and then here I would like to mention this call for action about that also in concurrency and in this kind of in these lines of work, we should try to mechanize things a bit more. Yeah. The last thing, and then I'll say I can stop so I can match Pavel's ending time. There are extensions of session types to probabilistic systems. So the whole idea is that when you have branching, instead of having, as I've shown you, like the O+, you add a probability distribution there. So you can imagine if P rise to Q, and then you have 2 branches. Now, instead of saying they could do branch 1 or branch 2, you also add a probability to it. Okay. And if you do that, then there is some work. Initial work is not really multi-party, so with the choreographies. But what they do there is that they are able they define a type system with this probabilistic session types, and what they're able to do is to give an upper bound of what's the probability of terminating of the program. And you do that in a pretty easy way because you don't analyze the code. You just have to type check. And then all you have to do is to reason about at the type level. Because what you can do, you can transform these types into Markov chains, which are basically state machines with probabilities embedded in this. And then you can use their theory there. And yes, and then now I'm actually working with someone on extending these ideas to these choreographic things. And one thing that we have done actually is to also define a sort of probabilistic choreographic language like this one. And then what we do is we map into Prism for proving properties. So I don't know if you heard about Prism. So Prism is a model checker. What you do there is that you can write probabilistic concurrent systems. And what it does, it will you can pass some properties there in a very abstract way. And it will compute properties like what's the probability of reaching this state, or what's the probability of terminating, which is also a special case, or what's the probability that some variable will get some value, or these kind of things. And what we did, we actually showed that you can define some choreographic language that then by means of projection is mapped into this Prism language. And then you can actually verify probabilistic properties in there. Yeah, then the last thing, I talked about this before, I said I had a slide. There is a strong correspondence actually between session types and linear logic. So all the questions that before Frank was mentioning, yes, you can do that. But actually there is someone from Javeriana who is really working on one of his main topics here. Do you know who he is? You cannot say it. Maybe you don't know. He's been away for a long time now, right? But yeah, it's Jorge, and he's coming. He comes from here, right, Frank? Yeah. Same university, right? Just one last thing, if you're interested, there is if you look at this link, you can just Google for it. There is a collection of implementation of session types in different programming languages. And that's it. I think I will stop.
So, Marco, one question that somebody asked me to. So you chose Erlang because of the WhatsApp grant, or why Erlang and no, I don't know, Python or some other functional language?
So there are several reasons. One is that we were looking for a non-type language where you could add some typing disciplines there without having to build a parser or something that actually does it separately. So what you can do, you can take any language and then write a parser, construct an abstract syntax tree yourself, and then write a type checker there. And we didn't want to do this because we didn't want to, because then languages change and everything, then it becomes hard to maintain. Another thing you can do is to actually we found out that we could trick Python into doing static checking on the fly. So what you can do in Python is that you can put annotations in the code, And this is part of all these languages that do some dynamic checks. And then what happens is that you can trick the Python interpreter loads the program to do some static checks. Because when it loads the program, it will look for all these annotations you put, and then you can specify in Python itself some code that works also with the abstract syntax tree. So we had a master thesis that they did this, and they basically managed to write a static checker for session types in Python. But Python is not really a concurrent language. I mean, of course, you can do that, but it's not really designed for that. I think it's designed for something else. And then we got in touch with some people at WhatsApp, and yes, then talking to them, they were interested in knowing how you could do it in Erlang, and because they use Erlang, so we just looked into that. But after all, I like the language. I like the Erlang language. But for these sorts of things, I'm not sure. Maybe you could do Golang. That would be also another possibility. There is already some work doing session typing for Erlang, for Go. But again, Golang is typed. And here you really have the possibility of playing with these gradual things that gives you so much flexibility.
More questions? Okay, we take our speaker. So there should be something here. Ah, ¿ya están? El refrigerio los espera. 15 minutos. Es comida para 80 personas. Ustedes son como
I would like to thank all the other expositors before me, as they laid some of the groundwork so that I can go faster, like statistics, the actor model, the Groot, and the Groot from the one that's not here anymore. Okay, so I also want to tell the story of how this model came to be. So I was first, when I joined Promova, tasked with two major things. The first was to extend one of the models, but since I was new in this topic, this was very difficult. Everything was like in a foreign language that you don't understand at all. So I went with the second task first, which was to implement um, the simulations for the grid model. And we wanted to make it support as many agents as possible, because the current models only supported very little, very small number of agents. So we started with Scala, and very quickly, as you can see, the complexities grows very big, and there's pretty much nothing you can do about it. So let's say you have n is the number of agents, m is the number of connections of each agent, and r is the number of rounds that you're gonna run the simulation for. And that's already 100 million, this of just 110,000. So it became very apparent that we needed parallelism. So I first started with the most obvious choice, which is threads, but this wasn't really satisfactory. So I moved over to Scala parallel collections, but also it didn't feel quite right. I also tried futures and promises, but it didn't feel quite right until I got to ACA and the, oh, I just did. Mhm. So I came to ACA, which is the actor model, and I finally started doing simulations with the actors, and it just fit perfectly because the actor model is essentially actors communicating with each other with messages, and that's how we communicate in chat. So you send a message to someone, and it goes to the inbox of your WhatsApp, and then that would be your mailbox, and you can read it sequentially, or you can, I don't know, you can prioritize, for example, your girlfriend or something like that. And the actor model already contemplates this out of the box. Also, it is useful for simulations and real communications. For example, LinkedIn and Verizon use ACA, and I learned that Erlang uses WhatsApp is used in Erlang with the actor paradigm. So it is easy to scale it both vertically or horizontally. So you can easily add more memory, and then you have, for example, if you double the RAM, you have double the number of agents, or you double the cores, then you almost double the speed. And you can add more machines because this is very compatible with distributed architecture, so it was pretty good. And I finally finished implementing the grid model using actors. So when you actually implement something, you notice some of the details that are real difficult to grasp when you're just looking at the paper, for example. So it really helped me to finally start understanding all the meetings and all the papers. So I want to ask this question now. We're going to take a little break. So which one is the longest bar on here? I don't know. Which one is the longest bar? I'm sorry.
What's longest? What does it mean longest?
Yeah, the one that's longest. Really? Isn't it D? No?
B.
D, no? Yeah, I think you're probably wrong. So, okay. I got this ray of inspiration, which was the spiral of silence. I actually found it on my leisure time when I was watching a YouTube video. And I came across that theory. So I decided to dig in deeper since it was very interesting, and I thought I could apply it to our models. And this is Elizabeth Noel Newman, the author of the theory. And she's a German political scientist. So what does the theory pose? It's that very essentially that the unwillingness to express an opinion that is perceived to be against the majority opinion. So if you're in the minority opinion, and then you're very likely not to speak up. For example, in some very, I don't know, very spicy topics, especially, for example, in politics, if you feel that you're in the minority, well, it could even be life-threatening to go against the flow.
Like
So,
Israel versus Palestine.
yeah, for
Palestine.
example, you can get beat up and all that stuff. And that is because we have a fear of isolation. That this is actually something we evolved with, because going out of the group could potentially mean, well, you have no help and you could get eaten by predators more easily. So this theory also states that there's an opinion climate, and we're constantly measuring it, which is just like think how the opinion is on a room. So you think, oh, they agree with me or do they not agree with me? And all of that on a societal level is what is called the public opinion. And that is basically what's perceived as the majority opinion, but it isn't necessarily the majority opinion. It could be a minority opinion that is being amplified. Okay, so how do we combine this model with the grid model? So first we have to find a model that's already been created. So I went to the literature, or well, I had to create one. So, but I first went to the literature, and after looking at many, I found this one that was very interesting. So this paper's name is really, really long. So it is a paper about measuring the impact of bots and how they propagate the spiral of silence. And the interesting part was that it proposed an agent-based model, so this fits very nicely with the actor model. The main focus of this is also on social networks, which comes in handy, but it had a little problem, and it was that it had a static opinion. So either you agree, which is 1, or you disagree, which is 0. And it was also a very interesting paper, so it wasn't boring, because it looked at the results of what bots do in social networks. And the thing is, they do propagate the spiral of silence, even if you just have a tiny amount of them. Okay, so these are the changes I made to the model. So I'll go very fast. First, it's the belief that we have. So it went from 0 or 1 to a number between 0 or 1, so that it can be updated by the group. We also created a new silence vector that simply represents, are you speaking or not? So 0 is you're silent, and 1 is you're speaking. Then I also created a tolerance radius, because I needed some way of knowing if you agree with someone. This tolerance radius is like a distance, and if you fall within that distance, well, then you agree with that person. But I also wanted to not have it always centered around you, but you could be able to move it. So, because sometimes, I don't know, you don't agree with the people that are further right to you or further to the left to you. And finally, we have the influence matrix, which, well, it is the influence each of the agents has on each other in the graph. So we also need an agreement function, which we generalized it. And it is simply a function that takes the indices of 2 agents and says to which degree are they in agreement. So it is a number from 0 to 1, but in our specific model, we defined a function called congruent that that is binary. So we don't have any degree of disagreement. So you either agree or disagree in our case. So with this, 2 questions arise. Okay, so what causes someone to shut up? Or and then what is the impact of someone deciding to remain silent? And so we came with 2 approaches for each one. The first one is based on confidence, then on majority, and the other has a notion of no memory and then a notion of memory. So we have 4 different agent types, which is the combination of them. And to determine silence, we have to determine a silence update function, which is simply a function that updates the silence vector. So we're going to get the silence vector of the next round. So basically determine who is going to speak or not. And let's now look at the implementation of this. So this was taken from the paper that I mentioned earlier, the one of the bots. So they have this implementation of confidence, and essentially all this jargon, what it means is that you have an opinion climate, which is essentially how many people agree with you. So if let's say 4 people agree with you and they are speaking and there's no dissent, then your confidence is probably going to go up if you have an opinion similar to them. But if there's disagreement, like let's say there's 4 in favor and 3 against, then your confidence might grow, but slower. And the same applies on the other direction. So let's say you have 4 against, and in this case, your confidence will go down. And so what happens is that we have a threshold, a belief expression threshold, and if you're over that threshold, then that means that you speak. And if you're below that threshold, then you don't speak. So the next one is a much more simplified version. This is the majority approach. It simply means if the majority of your neighbors are speaking, if they agree with you, then you speak. And if not, you remain silent. So now let's look at the impacts of silence. Now, this function is the one that modifies the belief. And it takes as inputs the current belief vector and the current vector of the people that are speaking. So now let's look at the particular implementations. So we have the memoryless approach, which this is essentially the case where someone faces backlash for their opinion and they delete their social media. So they go private or they delete their post and they cease to express their opinion anymore. So they cease to participate. And how we represent this is by multiplying here by either 0 or 1. So if you speak, then you're considered, and if you don't speak, then this value is 0. So the influence you have on agent I is 0. So this had a little problem, and is that you immediately forget, and at the next round you forget the one that was before. So you forget the one that was speaking.
This is just the groups. The new thing is the S, right? That's the only new thing.
Yeah, yes. So, but this brings some interesting properties. Okay, so now we have the memory approach. And the memory approach simply means that we have now a public opinion. And this public opinion is for the case where someone faces backlash, but they don't remove their post. They simply stop posting. And they will post again if the opinion climate is favorable again. So this is just traditional degrowth, just that instead of being with a belief vector, it is with the public belief vector. And how do we update the public belief vector? If you're silent, then you don't update your public belief. But if you start speaking, then your public belief is the same as your belief. So it is as if you made a new post. Okay, so let's look now at the current results. And for that, let's first look at the 2 types of graphs we're mostly interested. We look at the click. And this one is mostly as a baseline to prove some properties. And the other one, and the much more interesting one, is the strongly connected graph. And we also have an algorithm to generate these networks, these graphs. And they come with this algorithm, which I will not go into detail, comes with these properties that are observed in real-world networks, which is small word networks. This is basically the 6 degrees of separation theory that says that you're 6 people away from, on average, to any other person on the planet. It also follows a power law tail degree distribution, which is like the rich get richer. It essentially means that the majority of the users, so the majority of us, have very little followers. So we maybe have our friends and maybe some online people we met, and then there are some very few people, which are, for example, politicians, famous actors, singers, and they have a lot of followers. So this essentially follows this distribution. And finally, this graph was generated using a form of preferential attachment. And so we needed to have an algorithm that updated that distribution on the fly, and that was very efficient. So we also did that. Okay, so let's look at the current results. So currently for the memoryless confidence, then we have seen counterexamples where it doesn't reach consensus. It doesn't reach consensus either on the click or on the strongly connected graph. This would be true on, it does reach consensus on the grid, obviously assuming puppet freedom. And this notion of stability is if the graph actually comes to some static values. So it could diverge, for example, to two different values or n different values, well, or it could converge to a single value.
So how did you concluded that this not reach consensus?
I will show you later.
But through experimentation, is it already formally? Just to know.
Yeah, we found a counterexample.
Oh, yeah, we did, right?
I mean, yeah, I know.
Yeah.
Okay, so now for the memoryless majority, which we have studied this one more, and I will later explain why this happens. So for this one, we have more incognitos, but they are in green, so we're pretty much certain that they actually hold. So we're pretty much sure that the consensus is reached on a click, and that stability is also reached. Now for this one is the one that we have studied the less, but we already have a counterexample. And then for the memory majority, we also have a counterexample for strongly connected, and we're very close to proving that consensus is reached, since this is a work in progress currently. Okay, so now let's look at the examples. I said, okay, so this one is for the memoryless consensus. This one is for, yeah, sure. So memoryless means that when you're not speaking, you're not taken into account in the graph. It is almost as if you disappeared, if your influence becomes 0, for example. And I will then explain the memory when we go to that example. This is for the majority one. And what happens is that, well, look, we reach the census. So what this graph means is, well, if the circle is colored, then the agent is speaking, and if it is empty, then it is silent. So what basically happens here is that some agents that they behave like as a bridge between different agents, they always remain silent. So it is as if you have now two islands where they independently reach consensus. No, this one is not a click. Yeah. Okay. So I will show it here. This is not of the past example. This is an example to basically see what happens. So we have this island, let's call it an island, where they reach a consensus of 0. And then we have this island that reaches a consensus of 1. And we have this one which acts as a bridge. So its value is at 0.5 because it is the average of this one and this 2. So it will never move from 0.5. But it is way too far away because the tolerance radius is 0.25, so it will always be silent. And these ones will always speak because they always have someone that supports their opinion. So essentially, it is as if we have disconnected the graph. and we no longer have this link. So the opinions can't propagate from here to here. And that is one of the effects of silence. Okay, now let's look at the memory majority. And the memory was the thing that we don't delete the post, we simply leave it up. And what we can see that happens here, yeah, this one is easier to look at to conclude for them. This one is a click, and it's also a memory majority. So let's look what happens. What happens is that on the first round, they all see that everyone is, well, not everyone, but the majority is far away from them. So they decide to remain silent. And we can see that their opinions, the real beliefs are the lines, and the discontinuous line is the public belief. So the private beliefs, they almost converge here, and they get very close here. So they're very close to a consensus. But their public opinions are different. And this is something that we precisely see in the spiral of silence. So people decide to remain silent, and they don't know how much they actually agree. So they don't speak, and they never break that spiral of silence. So they remain in this way. Okay, so this is how the previous graph looks. I screwed up here the colors, but the labels are correct. So the one that is agent 1 here is also agent 1 there. In this case, if you wanted to look how the graph looks. And okay, now let's go to the future work of this. Some ways to extend this model. So we could further extend the model by adding different things to it. For example, making the model asynchronous, like Joan's paper. Also studying the impact of bots. For example, introducing a new cause of silence, so something that causes the agents to go silent, or a new consequence of silence, so a different function to update based on silence. We can also explore the combinations of different agent types. Currently, we're only considering them of the same type, but we can easily mix them. No problem, and that could be very interesting. And we could also apply the model to real data, which is something a student from here is working on. How to get from real data, or for example, Twitter, to put it on our models. And well, the final one that I missed here would be to also implement the confirmation biases, well, the biases functions onto this model, which is something another student might look into. So thank you very much. Are there any questions?
A quick question about the implementation.
Yes.
How fast is it?
Sorry? Oh, we can now, it is very fast to run it, but the problem is storing that massive amount of data that comes from it. So we're exploring different databases to be able to see what happens. But we have a mode of the simulator that is, you simply look at the beginning, and then you look at some very small samples. So for example, every 100 rounds, and that one is really fast. So we can get a network of 1 million agents in less than 10 minutes to finish, and even over 2,000 rounds.
My question is about how it will. I mean, do you think it will be feasible to do it with when you have the real data you were mentioning here at the end?
With the real data, so
If it becomes huge, basically.
Oh yeah, it could be feasible. That's the entire idea, and we're also exploring in parallel a way to have this model be implemented by matrices so that we can use GPUs to calculate it. But the problem of that is that it over-specifies it a bit. This one with the actor model allows for a bit more freedom of that.
More questions? It's broken. More questions?
You asked the question about some bars.
Yeah, let's go back to it. So I was basically betrayed by my paid actors. We were meant to trick you into saying that D was the longest one. It's obviously B. But we wanted to like show the power of the spiral of silence, because this is actually an experiment that was done on it. And it was basically, you were sent to a room with other 9 people, but you didn't know those 9 people were also researchers. And they will all go like, yeah, obviously D is the longest one. Like, how could anyone pick anything other than D? Are they dumb? They would become like really aggressive to someone that says anything other than D. So the only 15% of people actually answer with B. The others went with the flow of the group. Yeah, only 15%. Yeah, it was the other way around. So
More questions? Okay, speaking about real data, now we have a talk about that particular issue.
yes.
Thank you, David.
I was one of the big actors. They failed me. I was like, it came out of the blue, and I didn't know what to do, and there was a confusion between B and D, and I was like, what's going on?
I mean, Frank even said B initially.
Frank said D.
No, he first said D. Then he said, oh.
Fail. It's like, you forgot the scripts.
Scam.
No, yo intenté, te lo juro. Yo lo intenté.
David, ¿sabes si hay alguna manera de desconectar temporalmente aquí?
Hay un cable HDMI allí. Creo que si lo conectas, como que él cambia solo. ¿No?
¿Dónde está?
Sí. Windows D.
Vamos a intentar así. ¿Podría ingresar desde el computador? No, voy a ingresar desde acá. Tengo la presentación aquí.
The longest thing.
Petro 2022. Oh, no. It's gonna block you.
Sí.
Ponerle que la olvidaste y que te mande un numerito al celular.
No, es que tengo la presentación o... Ven y yo descargo de mi computadora y lo ponemos desde la USB. ¿Sí? Préstame la USB. ¿La USB? ¿Tú no tenías una USB?
No, ese era el control.
But can you not connect that laptop to?
Yeah.
Not directly to the projector.
Yeah, that's what I suggested.
Cable para conectar desde aquí.
It's this one. You can do this one. This is the one I used.
Okay.
Let's just try. Yeah, that works.
Thank you, Marco.
Thanks. No. Hello. Okay, so as my partners are telling you about models, now I'm going to talk to you about how we use different models to classify text and some other ideas to extract real data from social media. So I'm going forward to this presentation. First, I'm going to tell you what is the problem or the main problem we have at this moment. Talk to you about a little bit about the models we are using at this moment and some of the ideas or the work we are doing at data extraction. So what is the problem we are at this moment or what we are doing? So people are able to express their opinions on various topics in different ways. On social networks, it's very common to use text. So as my partners, colleagues have told you before, they're using actually values like numbers, but in social media, the opinions come in a different way. They come like text, they come from, or they could be images, videos, audios. So the thing here is, in order to use the models to measure the polarization of a network, it is necessary to convert, we are focusing in text, into values that serve to represent a person's opinion on a particular topic. So the question here is how to convert text or opinions into information that we can process or we can use to measure polarization.
We were supposed to have another presentation previous to that on measuring polarization. Unfortunately, the speaker got really sick, and he couldn't come. So basically, the talk was about the measures we have developed to measure the opinion of a community, to measure the polarization of a community, where their opinions are expressed with numbers between 0 and 1. Okay, 0 strongly disagreement, 1 strong agreement, and the higher the value, the higher the agreement. So that's it.
Okay, thanks. So as I told you before, we are using some models to get a value from a text to estimate the opinion of a certain topic. So we are using some natural language processing models as a tool to achieve this objective. So little bit about the models. Currently, there are a lot of models that serve to classify text according to a level of favorability regarding a topic. However, it's not a simple task. If we look at text, we can it could appear some text that could be sarcasm. Text come from many other languages, so it's not just pick one model and use it to estimate an opinion. So there are so many factors we have to consider in when we select a model. So here appears other questions. So how can we make sure that a value represents the correct opinion about a specific topic? And how are we make sure that these models are correct for most cases? So that's one of our first work as in this work in in data. And what we did is from a set of real data, um, first select some messages from a data set and manually classified some of these texts. So we can later compare with the results that we get from the models. So there are so many, as I told you before, there are so many models to achieve this objective. And we can consider, or we interest more about, could be ChatGPT, some models based on BERT, some models that uh, were created to sentiment analysis or some task like this. But one interesting thing of certain models that some models are allowed to include context. As a context, I mean to include a little text or include a little information about what we can or what we want to ask to the users. For example, we might ask about what is the position about the Palestine war in some data set and in specific. So we can have like a data set of many data and try to change the question and add a context to ask for many things in the data set. So that's one interesting thing of certain models. About the data set, we used the data set to be tested come from a social network. It's actually X, and correspond to people's opinion about the US presidential elections in 2020. A subset of 15 messages were selected. The comments are original Spanish, as I told you before. Maybe some models are sensitive to the language, and we've these 50 messages in Spanish. A context related to the topic was defined. The context is actually below. And the context introduced the experts to the topic in order to do a manual classification of each message considering the Likert scale. So number 1 represents strongly disagree, 2 disagree, 3 neutral, 4 agree, and 5 strongly agree. So the context or the issue to be classified is, do you agree with Trump's candidacy? Is something like that. Mhm. So I don't want to get much into this, but there are some of the models and the context we use. So I skip this, but I want to show you some of the results we got some from the messages. So first, from the manual classification, we calculate the mean, mode, median, and standard deviation of the manual classification. So here are some of these values. I have to excuse because they're in Spanish. And we use every selected model to classify each message. We actually look more than 5, but we just use this 5 model for this presentation. As I'll tell you, the models are ChatGPT and some interesting models that allow us to include a context. So some results, or in some cases, the classification match with the experts classification. So in this message, for example, the expert says the message is strongly agree with supporting the Trump candidacy, and the models give the same results, at least most of them. There is another example, not only strongly agree, also in a neutral position. There is an interesting example of sarcasm. These texts include some sarcasm that the experts consider they are the message or the people, the post this message is agree to the to 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 Trump's candidacy, but the models uh, do not um, catch the it it, the opinion, right? See, sorry. So this is one of the examples about sarcasm that we have at. There are models, different models, not only ChatGPT. There are other models. See, yes, I think the model one is ChatGPT. So after we get the results for every single message, we try to evaluate the results that we got. So in we can see at in this table that maybe or actually model one, that is ChatGPT, give us or at least have the least percentage of error, or I mean it has an 80% of accuracy or precision about the classification. So actually in ChatGPT we use the 3.5 model. Actually there's the ChatGPT 4 that we also do some tests and is even better than ChatGPT 3.5. So uh, it doesn't appear at this table, but I want to add that. Okay, some conclusions about the models are, as I told you before, I didn't try different language, but with some other models that actually was trained in English, and we tried to classify the message, obviously it didn't work. So we noticed that models are language sensitive. Uh, Also, as I told you before, sarcasm is difficult for models to understand the to understand. Even sometimes it is difficult for us to understand the message. So yeah, that's true. So another thing is the model is capable of use context allowed to understand, to better understand network opinions. So one interesting things of using context, as I told you before, is get a great data set of different topics and ask using the context about any topic. Could be uh, politics, economics, healthcare, and not focusing only in extract data for a certain topic. So this could be interesting. Also, the way in which the question are made, the context is written, affects the answer of the models, and this is something that appears recently in this kind of AI models that it's called like prompt engineering, the way in which we write the questions to these AIs. And so this is much about the models and the classified the opinions we did, but actually we're trying to get some data um, from Colombia and start to study some the polarization in Colombia about a certain topic. So um, uh, we are collecting data regarding a politics issue, and the line or the idea is first classify the opinion and then use the models to measure polarization. So um, there's a lot of social networks, and could be Instagram, could be Reddit, but X can be a good choice for many reasons. First, X, at least most of the posts are text, so and we are only focusing on text. The X also is very polarized social network, and the way in they transmit the information, it is easier to see how the users interact between each other. So there are other reasons for X to use X, but we think this is the right social network to study. Currently, getting data from X is not quite easy, especially since Elon Musk got X. There are a lot of new politics and terms and conditions to extract data and try to do some studies about it. Anyway, it is possible to get some data by getting access to X API, but um, the resources we have at this moment do not allow us to get so much data to do some studies about this.
We are paying for it, right now.
Yeah. First, we like a month ago, we just start getting some data using the X API, and we have at this moment like a 10,000 messages to see how the polarization is.
There is a restriction on the time, right? Like 1 week or something.
Yeah, at least at the level of access to the API we have,
Mhm.
we only can see the last 7 days of the message published. So we are trying to 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 establish like a window of 7 days and extract per week some messages to use the to extract all data, all possible data we can. Okay, some future work we are trying, or my interest is continue studying new models to classify opinions, considering not only text, as I told you, in social networks. People can post also images, videos, audios, and it could be interesting if we can classify this kind of post. Study the dynamics of opinion in the networks and how they change over time, as well as the main topics discussed among users. And also estimate influence and confidence among users considering other information from social media, like interactions between users. This is more for try the models that David told you before, that in some cases need the influence and the confidence that the users have. So that's all about data I have. I don't know if you have any question.
Any questions? Okay, there.
Um, Seriously, I don't know if I didn't hear it, but how you classify what information is relevant for the model or no? Because, for example, in social network like X or Twitter, it's common find comments like, for example, Donald Trump is an unicorn. How you know this is relevant for the model?
Okay. First of all, we can use the context to like filter this kind of message. Of course, we also interest in the interactions between users, and these kind of messages could be interesting to classify also. But in the way we can just discard this kind of message, or before applying the models to classify, we could like check the topics, the main topics, using different algorithms, not necessary AI models, to check the topics and then discard some messages. So there's a way to do that.
So you used several different classifiers, but I'm a bit more interested whether they had like different behaviors between them, or do they all agree within them? Were they all about the same, or is it ChatGPT way better than the other ones, or what happened between them?
Well, the models are trained with different data. So ChatGPT is one of the, or at least it's a model that was trained with a lot of the information. Um, the models actually not only, how can I say?
Do you sometimes have complete disagreements between the models, like once it's 5 and once it's 1?
Yeah, that could happen. So that's one reason we want to try different models and try to get the one which give us the closest estimation of the value.
Okay, thank you.
Now you're extracting the data like from the how can I explain it? How are you going to extract the data of the changes of the opinions between the time?
There's a good question. We're only at this moment we are only trying to extract the data. So if a user could post not only once, he could post twice in the window we are extracting or getting the data. Um, there's a topic we must study because at least the different papers we read about these kind of works or this kind of idea, we at least we don't have an idea how to do it. So we are at this moment uh, have this problem to solve at this moment. Okay.
More questions?
So does the if you pull like a tweet from X, does it come like with metadata, like for example the username or something like? Oh, so you could use that to like see how the opinion changes over time, right?
Yeah. We can get not only the text, we can get when it was created, some information about the interactions, how many times the post was retweeted, how much likes, the mentions we can see, which user was mentioned in the message. There's a lot of information we can get, not only the text, and this kind of information could be interesting to use to calculate, as I told you before, to estimate influence and confidence. So we are also trying to get more data.
Okay, so I wanted to ask about how did you come up with the initial question for ChatGPT? So for the context, how did you came?
How we select a context,
Yeah,
how we
did you
define
select the
as a context. Okay.
Like the
First, actually, we try different things. First, we in the group we tell, or we say, let's try it and use this context. Also, we have tried to to tell ChatGPT, give us a context about this, and we tried that context, and and we try to see if a more complex context could give us like a better classification. It's not necessary. As I told you before, the way in which the question is made can also affect the result of the model.
Isn't that relevant? The context.
More relevant?
It isn't that relevant?
Yeah, at least the way in which you write the context may affect the result.
I think we can close here and you can discuss further with him outside. Would be nice because it's 5:15. Okay, thank you everyone for having come here, and thank our speakers, all of them, and
thank you to Frank for organizing this.
let's hope to this every year for the students.